Good morning, good evening, good afternoon, from wherever you're joining us from. Welcome to day 2 of the IBM Research Horizons event, focused on the future of climate. I'm George Selewski. I'm a research scientist. I'm also the manager of the Think Lab here at Yorktown Heights at our research headquarters. We have a great agenda for you with our leading scientists in our climate initiative, and we're just so happy and delighted that you're joining us. Before we start, I just have one housekeeping item. If you're joining us via the platform, you should see a chat to your right of the video. Please use it. Our scientists are online. They're eager to interact with you and to answer your questions. And even for the pre-recorded sessions, we'll have our speakers on live immediately following the session to answer your questions live. So please use the chat. If you found this video just through YouTube, you can also join the chat by clicking on the link in the description that will take you to a registration page. You can register for the event, and then you can also participate in the chat. So with that out of the way, the theme for today is adapting to climate change and the role of research and technology can play in helping businesses and organizations adapt to our changing climate. I can't think of a better way to kick it off than to have Dr. Hendrik Hamann, who is our chief scientist in our Future of Climate strategy and a distinguished research staff member here at the Yorktown Heights Laboratory. Hendrik, how are you? Good to see you.
No, I'm very good. Thanks so much, George.
So please take it away.
All right. So yeah, also from me, good morning, good afternoon, and good evening, wherever you are. My name is Hendrik Hamann. I'm the Chief Scientist for the Future of Climate here in IBM Research. And yes, I have the privilege to kick off our second day of our Horizon event of the Future of Climate. Marcel, please push out the presentation if you could. Yeah, let me start sharing some interesting but perhaps worrisome data, which I think says a lot about the future of climate. Although this is actually data from the past, you will see similar data later in the IBM presentations. Not because we like to repeat, but because this data tells a very complex story. What is shown here are the observed temperature distributions during summer for each decade from 1950s to 2010, where the distributions are normalized by the local standard deviations observed way back in the 50s. So you might wonder what the magnitude of a standard deviation is. It's around 3 degrees C, but of course it's different in different locations. So what is this data telling us? Well, first it tells us the climate between 1950s and 1980s did not change much. The distributions stayed the same. It became neither warmer nor colder. It became neither more extreme nor less extreme. It also tells us that starting in the 1980s, there are suddenly drastic changes which have accelerated. It tells us that it is progressively getting hotter, but not only that. It tells us that the extremes are becoming much more pronounced, right? The distributions are widening drastically, and that's certainly a big concern. But what does that really mean, right? So for example, during the 50s, the average summer heat in New York City was 24 degrees C, with 3 or 4 days above 30. Today, the average summer heat in New York City is almost 1 standard deviation higher, and we have roughly 20 days of heat above 30. And 3 to 4 days above 35, which used to be 30. Now, while these trends are striking, the data does certainly not tell the whole story. What climate change really means, right? The impact of climate change will be different in different locations. It will be different at different times. It will depend on how much you prepare, how vulnerable you are, how much your business is exposed to such risk, how much resources you can spend on preparing, how much time you have to adapt, and many other factors. Now, yesterday, on day 1 of our Horizon event, we asked the question how information technology, AI, machine learning can help with mitigating the impact of climate change, slowing or even reversing the trends which we've seen on the previous chart. So whether this is by removing carbon through materials innovation and carbon capture, whether this is by improving the carbon performance of business operations such as order fulfillment, cloud computing, business travel. Today, we'll focus on the adaptation to climate, to the impact of climate change. And what is important is that this is not a simple choice between mitigation or adaptation. Clearly, we must do both, and that is why we do research in both areas, in mitigation and adaptation. In fact, I want to spend a few minutes discussing the fact that the technology opportunities to advance both the mitigation and the adaptation are driven fundamentally by the same underlying trend, which will provide context for today's discussion, but also to yesterday's discussion. Now, what is the underlying trend enabling us with mitigation and adaptation in technology? Well, the trend is that the data and information we have today about our environment, our physical world, our climate, is richer, deeper, and bigger than ever. And that is because of continuous technology innovations, which we've all witnessed at a minimum as consumers. Data from the environment, data from the Internet of Things, from sensor networks, from satellites, from drones, from cell phones, is growing exponentially by something like 40 exabytes, 10 to the 18, right, bytes per month. So vast growth of data and information. Now, what does this trend then do, and why does it matter to the future of climate? Well, this trend digitizes our physical world, our environment, our climate. And that is really the foundation to model, analyze, apply machine learning and AI to help to make better decisions and improvements, right? How to sequester carbon in the soil, how to prevent methane leaks, or how to forecast the next drought and predict its economic impact on a community. It may be also important to remind you that digitization of a sector or industry is nothing new, right? Other sectors and industries have been almost completely digitized. Think about media industry, the finance, social networks. So why am I mentioning this? Well, because history has shown that digitization enables through AI, machine learning, cloud computing, massive efficiency improvements. And that is really the opportunity we're talking about in this conference. Now, the environment, our climate, the physical world is arguably one of the most difficult ones to digitize. It actually may be one of the last frontiers of digitization, which holds the promise, but also the opportunity to discover the required knowledge from all the information which is growing every day, so we can make better decisions on how to battle climate change most efficiently. Let's have a look at what we heard yesterday and what we will hear today. If you think about the role of technology, there are many. However, one of the key benefits of cloud computing, AI, machine learning, and some of the techniques we're talking about today is that we can accelerate the discovery of finding the best solutions for battling climate change, whether this is adapting or whether this is mitigation. To do this, you follow a process, and that's very much the same process you use for scientific discovery, right? You must first learn from all the information which is out there. Then you ask the questions, you hypothesize, you model, you test, and then you go back around. So if you think about what you heard yesterday, you heard how we can learn faster using AI to find new materials for carbon capture. You heard how we can model much faster carbon footprints and carbon performance. And finally, you heard how we get answers to our questions through testing the solutions in the marketplace through applications. So today, we follow a very similar pattern. We start with core technologies, which allows us to accelerate the learning from all the data with our geospatial capabilities, with our modeling frameworks for climate risk and impact. We then discuss AI and machine learning approaches to accelerate climate impact modeling. And finally, we show how we apply these insights and test these solutions in the real world, and then we come full circle around. Now, let me stop right here with this great quote from Nelson Mandela, which is, I think, a stark reminder of what we should not forget. There's really no better way of saying this. Please read it and don't forget. This quote also provides a great transition to our keynote speaker, which we're all very excited because it's not only an outstanding individual and leader, but for sure he will fire us up with his passion. And George will introduce him next, and back to you, George.
Thanks, Hendrik, and thanks for a great talk. And As we go through the day, especially later on in the day, we're going to hear more and more about those technologies that you're referring to in that kickoff. But as Hendrik said, we have just an outstanding keynote address coming up. You know, this event is focused, of course, on technology and innovations and how technology can help us mitigate and adapt to climate change. But I think we can all agree the real ultimate purpose is to positively impact people's lives, especially those that are most vulnerable to climate change. And so with this larger purpose in mind, it's an absolute delight to introduce our keynote speaker, Mr. Ibrahima Cheikh Jong, who is currently the UN Assistant Secretary General and Director General of the African Risk Capacity Group. This group was formed by the African Union and has delivered over $720 million of insurance coverage to over 72 million people. Just tremendous impact on the continent. Prior to his current role, he's had several leadership roles, including in consulting at the African Consulting and Trading Group, banking at BNP Paribas, and in government, where he served as a special advisor to the President of the Republic of Senegal. So we're delighted to have you, Mr. Jong. It's great to see you, and we can't wait to hear about all the wonderful work you're doing with the ARC.
Thank you very much, George, for that warm introduction. And also a big thank you to Hendrik for making my life easier in making the case about the gravity of the situation when it comes to extreme weather. Let me, before I bring you the voice from Africa, where I'm based right now in Senegal, let me express my gratitude to IBM for helping us to make the case from Africa and bring in an African perspective, but more importantly, a human perspective of climate change. It is extremely uplifting to see that we can actually build public and private sector partnership with IBM so that we can combine our forces to help the communities across the world. Let me make 4 important points. Number one, just walk you through some of the problems we're trying to address, particularly as far as Africa is concerned when it comes to climate change. And then second, the mandates have been given to my organization by the African Union to address those concerns. But our approach to working with a greater partnership to make sure we can provide some practical solution to Africa. And as George said earlier, we've been quite impactful, but the impact goes beyond just monetary impact. I'd like to walk you through also some of the great value addition that we provided to Africa so far. And obviously, the most important part of the conversation, as George said earlier, is to see going forward, how can we collaborate with organizations like IBM and other technological companies to make sure we innovate the way we actually profile risk on the continent. I think on the problem, if there was any doubt that we're dealing with extreme weather situation, you just have to watch the flooding situation in the US, the flooding in Germany, and recently also in Africa, just to demonstrate not only the Earth is warming up, but it's creating tremendous challenges to many countries, including developed countries. I think second, what is not obviously hopeful is the fact that I think I lost, can you hear me?
Yes, we can, absolutely, we can hear you.
I think what is not absolutely optimistic is the fact that, as Henry said earlier, unfortunately, the Earth is actually warming up. So we're not out of the woods yet. And the question is, how do we anticipate and making sure before this disaster occurs, we can take the necessary measures as well. Now, if I bring it down to Africa, the problem I just talked about are very specific problems that we're dealing with. And that is when it comes to drought. In many parts of Africa, particularly in the Sahel region, drought causes tremendous problem in terms of food security, but also in some cases, pushing communities to get rid of their assets so they can survive and take care of their families. and be able to keep them in school, in some cases also be able to generate some incomes as well. We're also dealing with tropical cyclone, which is a major problem in Madagascar, in Mozambique, again, with a similar human aspect across Africa. And obviously, flooding remains a major challenge in Africa because of the climate change situation. So because of all of that, we've noticed that what doesn't get talked about quite often in this conversation is the human face of climate change, even though Africa contributes less to the pollution and the warming up of the earth, but yet we happen to be suffering the most when it comes to climate change. So the big question is, what is Africa doing about what I just talked about? In 2012, the African Union has decided to lead by creating an institution called the African Race Capacity, entirely dedicated in making Africa more resilient in dealing with the impact of climate change. The way we do that is what I call the 2P and the 1R. The 1P is about helping countries to actually profile their risk with the hope that visibility allows government to decide whether to return some of the risk or to transfer the risk to the insurance market before it actually occurs, because it may be too late when it happens. The second P is the preparation of the government, particularly the different government services that are involved in responding to disasters. And oftentimes, a lack of any coordination at the level tend to affect the life of many Africans sort of going forward. So therefore, coordination is key. And last but not least is the response. And that is that what are some of the financial resources that can be mobilized through insurance by transferring the risk that allows government, in addition to the national budget, to have access to additional resources in a speedy manner. And this is, in the context of Africa, extremely critical, because when there is a drought, while you wait for the international community to come to your rescue, people are dying, lives are affected, and livelihood are also affected as well. So therefore, it's really important to show that face. In fact, yesterday, I spent the entire day visiting with the communities that have benefited from our support in the past. And it was very heartwarming, it was inspiring. It was also extremely emotional just to see how some of these communities, if it did not come with the support, either they would not be surviving or their families would be affected as well. So the question is, what has been our impact since we got started? Because it shows not only the potential in terms of our intervention, but it also demonstrates that the concept has been tested, there's a proof of concept, and we can scale up across Africa going forward. I think number one impact is the value addition that we provide in convincing African governments in the importance of early warning systems. Disaster does not discriminate, and if you wait till it happens, it may be too late. So I think slowly and surely, we're building the culture of disaster management, of contingency planning, so government can actually be prepared before it happens. I think the second impact I see is the way we are empowering African governments to be on the leadership front in dealing with disasters. In other words, we can provide all the support necessary, but ultimately, government has to decide how much of the risk they would like to transfer, but also how much they are willing to coordinate themselves so they can get the necessary capacities to react to the needs of the communities. I think the third impact that we have, and that is our ability to model the risk. I mentioned earlier, we've been known for quite some time in modeling the drought risk in West Africa, in other parts of Africa, to a model that we designed called Africa Risk View, which allows us to use some data and anticipate 2-3 years down the road when drought is going to happen based on the rainfall in that particular country, and assess the impact it has on the communities and be able to anticipate. As of today, We've launched a tropical cyclone product. We're in the middle of designing a product in flooding, and we have had some good conversation with IBM to see how we can actually leverage and your know-how to be able to actually add as many products as possible so we can respond to the demand of our member states. I think the issue of number 4 is modeling. In today's world, any disaster, extreme weather, can be modeled. And I think I'm preaching to the choir here, knowing that the majority of the audience are scientists. You believe in the power of modeling. I think what is important for us, beyond just the academic exercise, is the ability of how modeling can help our member state to anticipate, transfer the risk, and use that information so they can make some sound public policy decision as well. And last but not least is the financial payout that we provide. As I said earlier, when the country decides to transfer the risk through us, what they also do is the possibility, if that disaster actually happened and triggered, they can get a payout in the early stage, which allows them within 2-3 weeks of the disaster happening to get money, which they can use to support the communities that are vulnerable across Africa. And I can assure you, based on the visit that I did yesterday, talking to some poor communities in Senegal, it saves lives, it saves livelihood. So this is not a joke when it comes to climate change on the African continent. And our job is making sure we protect them. Now, I'm mindful that the scientists I'm talking to here attach a great deal of importance to mitigation and adaptation. But Africa also is dealt with the issue of resilience. And what I have just described so far is to make Africa more resilient while we're looking at investing into adaptation and mitigation as well. Let me wrap up by saying a couple of areas where I see we could work together with institutions like IBM and others. Number one, you obviously are the leader when it comes to using technology and modeling. And I am confident with the discussion that we're having, we can certainly leverage on your track record and know-how and using technology to actually anticipate and predict some natural hazard. That information, as I said earlier, in the case of Africa, is extremely critical in saving life, but also making some sound decisions as well. I think second area where I see some challenges as far as concerned, our modeling has to be accurate. It has to be in a way that when we go and talk to the government, there is no ambiguity whatsoever of what's going to happen 2 years from now. Because the type of disasters we're dealing with, they're not as frequent as you would expect them in Africa. And that's the reason why we can anticipate and be able to actually model them. So we certainly will look forward to looking at your modeling capabilities so we can model the disasters and be able to have a timely response in due course. I think it's very important that with your know-how, given that in many African countries, there's so many competing needs in other sectors whereby to get them actually focused on the impact of climate change, it's a bit daunting. In some cases, we're using a lot of advocacy to convince them to take it more seriously. But I believe with what you bring in with technology, we could certainly be able to use that evidence to demonstrate that if you're dealing with this type of disasters, when you wait till it happens, maybe too late. So convincing by evidence is really something that's important. I think to wrap up, as going forward, we are absolutely committed, in addition to our partnership with the public sector, to work with the private sector to develop a different type of PPP. In this case, you being the private sector and the government that we support being the public sector. But we also come in as a continental organization, so we can use our mandate and your know-how to be able to support Africa. We're very much committed to exploring that opportunity as well. I think second, most of our donors that are supporting us provide what we call financial support. But what this organization needs to grow is also technical partnership. We need to build our capacities of our R&D department to make sure it could model the risk. So any obviously offering that you have in making sure that we can build our technical capability It will make us credible. It will make us much stronger to support our member states. We are certainly takers. I think last 2 points to say is that we are also interested in building our own capabilities in co-developing product. So it's not just a matter of transferring technology. I'm also interested in the transfer of know-how. So if we can actually co-develop some of this product, it allows us to actually bring in the African perspective, the reality of Africa, the ecosystem of the continent, so that the product that we design can also help us to further respond to the African countries. And I think last but not least, there's so many developmental organizations, such as the World Bank and other multilaterals. They are doing similar exercise. It is about time for us to join our forces so that we can have a menu of solutions matched to the demand of Africa so we can be helpful. So my takeaway message is the following. What I just described, if there's one thing to remember, is that what we do save lives. And what we do save the livelihood of Africans. So therefore, ultimately, unless we can demonstrate that all the work we're doing can lead to make Africa more resilient, protect life, we're not being successful in our mission. I am committed to doing that. I have no more hair because of that. And I have no doubt together we can join forces and bring the support that Africa needs so that Africa can also be more resilient. So thank you very much. And over to you, George.
Thank you, Mr. Jong, for a wonderful and an inspiring talk. You know, if we have time for a couple of questions, listening to your talk, a couple of things came to mind. One, you know, you alluded to technological innovation, financial innovation, and modeling risk, and then a sort of political, I don't want to call it innovation, but you know, empowering local governments to act. And I'm just curious, from your leadership position, which of those three create the largest barrier that you see as the most difficult to overcome, because they're very different and they're all critical to the success of your mission. So I'm just kind of curious what keeps you up when it comes to those three areas.
Yeah, the short answer is all of them keep me up. Now I think that's just they really go together. If you look at, for example, technology in Africa, one of the biggest challenges obviously is the fact that the access to the internet and other infrastructure in the IT system makes it quite challenging to come up with something that's like suitable to the African model. And I think second, on the modeling side, the using active technology or modeling to make public policy decision, it's not something embedded in many African government way of making decisions. So therefore, we have a lot of work to do through advocacy by demonstrating to existing trusted actually concept whereby what we do can save lives, and use that to convince African governments to believe in the use of technology to model the risk and eventually make the right decisions to go forward. But obviously, George, all of that has to be combined with a strong political commitment. So one of my big jobs is to really convince African heads of states that they become our champions about the power of disaster risk management.
I imagine that all of those quite challenging, but based on the impact the organization has had already, I have no doubt that coupled with your leadership, that we'll see even more impact ahead. I was really I love the way you described your thoughts on collaboration, not just technology transfer, but know-how transfer, and working hand in hand, co-developing technology so that you not only get a piece of technology, but the scientists and the researchers in your organization and organizations throughout the continent actually gain the know-how as well. And so I'm just curious if you have additional thoughts on that model of collaboration. Also, for those technological institutions out there, IBM and others, how to get involved and how to kick off a collaboration like that.
Yeah, but I think the number one message is important, George, to mention, and that is that we have the continental African mandates to do what I just described. Mm-hmm. But the solution do not exist, all of them actually within the organization. So we have to partner with others to actually fulfill that mandate. So that's the number one statement to make. I think second, to IBM, other technological companies, it's not just matter of just using what you offer. The question is, how do we adapt them to the African reality so we can actually respond to the needs that I described earlier? So I think what the discussion we're having with IBM right now is really the right approach. We've been having discussion with them, understanding our ecosystem, understanding our demand and our need, with the hope from that exercise, we can lead to co-development and eventually building our capacity so that there is a legacy that actually comes out of the conversation we're having right now. We're very much open, obviously, with other technological companies to do a similar exercise. But I think co-development is really the key because it builds ownership, it builds legacy, it builds leadership, and that's basically the way we see it.
Yeah, that's wonderful to hear. And I think quite like-minded in that way. I mean, we really strive in our partnerships. It's not about just building something and throwing it over a fence. It's about building it together, transferring the know-how and the technology, and then bringing the local expertise to inform the technology itself. Well, I think we're out of time, but thank you so much for your presentation. Thank you so much for your leadership in this area. We're looking forward to working together and also to hearing about the great things to come from ARC in the future.
Thank you very much, George. I wish you a great conference and look forward to the outcome. Thank you.
Thank you. Thank you so much. Okay, so we're now going to move on to the technical sessions where we're going to focus on technologies developed by IBM and IBM scientists. Again, focus on climate adaptation. The talks are pre-recorded, but the scientists are on live to answer your questions in the chat. And then following each presentation, they'll be on live to do a live Q&A. So something to keep in mind. Our first speakers are Anne Jones, who's a research scientist in our UK laboratory, and Johannes Schmuda, who's a research scientist in our Yorktown Heights laboratory. And the title of their presentation is Geospatial Analytics for Climate Impact. So with that, we'll let them begin.
Hello everyone, and thanks for joining us. My colleague Johannes Schmuda and I are here to discuss and demonstrate how geospatial big data analytics and AI-enhanced impact modelling can address the challenges of climate change adaptation by quantifying climate risk at scale. So the impacts of climate change are already being experienced across the globe. Climate change causes more extreme weather, changing both the severity and the frequency of extreme events. As the global climate warms, temperatures we consider extreme are occurring more frequently and temperature records are being broken. Heavy rainfall events are becoming more frequent and more severe. Rising sea temperatures are increasing the intensity of tropical storms. And rising sea levels are increasing the risk of coastal flooding. So the impacts of climate change are the downstream consequences to communities, infrastructure, agriculture, and other systems. And climate hazards are the weather and climate events, heat waves, floods, droughts, windstorms, wildfires, which cause these impacts. And climate risk is the potential for losses due to these hazards. So from coastal flooding, disabling critical infrastructure, to prolonged droughts disrupting global food supply networks. This graph shows the frequency and the cost of billion-dollar weather events in the United States from 1980 to 2020. And 2020 set the new annual record of 22 events, and it was the 6th consecutive year in which 10 or more billion-dollar weather and climate events have occurred. So these changes are unprecedented in time, in location, and severity. So we can't rely on existing approaches based on past experience to mitigate them. But fortunately, there's an increasing volume of data, climate and geospatial data, and sophisticated models of a variety of forms which can be deployed to help us quantify climate risk and build resilience. So what does this mean for businesses? Well, climate change adaptation and risk mitigation means building climate intelligence into operational and planning decisions. And here are a few examples across industries. Energy and utilities require both physical infrastructure to be resilient, which means climate risk needs to be quantified for that infrastructure, and operations to be resilient, which means building climate risk into planning and operational decision making. In finance, the management of financial risk requires a quantification of physical climate risks affecting your portfolio, which in itself may be diverse across assets and industries. And in consumer goods and retail, supply chains are impacted by extreme events, disruptions which need to be prepared for. So climate impacts business decisions across timescales, from responding to events that are in progress to predicting individual events days and weeks ahead, to looking at longer term predictions of the probability of impactful events over a season or years ahead. Weather and climate data and models are available to address all of these timescales, but applying them requires highly specialist, technical and scientific knowledge. So here at IBM Research, we've been considering how technology can help streamline this process without losing fidelity or flexibility. A further challenge that's relevant to businesses is the spatial scale. So weather and climate impacts are experienced locally, so changes need to be quantified in a locally precise way. But the domain of interest can be at the country or the continent scale, so solutions need to be efficient and scalable. So how exactly do we quantify climate risk? So to quantify climate risk, we need to combine hazard, exposure, and vulnerability. And to quantify the climate hazard, models of a variety of types, so physics-based simulation models, machine learning models, for example, are needed to generate and predict climate extremes and quantify hazards, so flooding, wildfire, drought, heat waves, etc. And these hazards then need to be combined with exposure for a given user or application. For example, the geographic location of physical assets or communities relative to flood risk areas, or the properties of a building which may be impacted by storms. And then to calculate the overall risk, a damage model needs to be used to map the hazard severity to damages or financial costs. So here at IBM Research, we've been developing tools and frameworks which enable us to better quantify climate risk in a flexible, scalable way to address some of these challenges that I've mentioned. So I'd now like to hand over to my colleague Johanna Schmuder to demonstrate how the IBM PAIRS geospatial analytics engine can rapidly bring together the diverse geospatial data sets needed by researchers and analysts to quantify climate risk.
Thanks, Anne. What we're looking at now is something we're all too familiar with. This is the general trend in annual temperatures, and this particularly case for the conterminous United States for the last 40 years. The trend line we added here shows a warming of something like 0.023 degrees Celsius per year. This development in turn drives other change, such as rainfall. So what we're looking at here now is aggregate rainfall across the United States. And again, you see a change, you see a trend, which is not quite as pronounced, but still there. Now, a key question for us is how to make business decisions in this reality. This regards both the question how to contribute to avoid further warming, but also how to understand our changing environment and how this affects our assets, our supply chains, etc. This, of course, is a spatial problem. You need to be able to process large amounts of geospatial temporal data to understand how different assets in different areas are affected by this, which is why our and our clients' work here is powered by our geospatial big data platform, IBM PAIRS, which I will demo to you in the next couple of minutes. What we're looking at now is the web interface to IBM PAIRS. PAIRS hosts some 6 petabytes of curated and analysis-ready data. What we're looking at specifically is the data that was used to generate the temperature time series we looked at 2 slides ago. Specifically, this is data from the PRISM initiative, which shows daily temperatures and rainfall amounts across the United States at something like 4-kilometer resolution. Crucially, this data obviously depends on time, okay? And what we're looking at here is a snapshot, actually is the aggregate for 1 year. So, if I click somewhere here, I actually sort of make a database request and PAIRS in real time to go back to the back end and pull up the time series now for the entire 40 years for this particular location. So you can see this is already nice. I can basically explore different conditions across this entire 40-year range across the United States. And of course, while I'm showcasing the United States for this demo, this is an entirely global project. This is an entirely global platform. You could also work outside the United States. Now, we were saying temperature is one thing. And as I said, this particularly is the data we used to generate this time series, and we crunched this with pairs for this. But of course, there's also things in here like precipitation we said here. And again, now we see rainfall aggregated over 2020 for the United States. At the same time, now you have the rainfall time series for these various locations. So you can see the differences between, what happens here in the Midwest versus what happens in the Rockies, etc. Now, pairs contains many, many data layers. The whole point is that we don't have just the data from PRISM or data from other data sources, but there is satellite images, there is aerial photography, there's land use data, weather forecast, etc. And all these things are trivial to join. There's no data fusion. It's entirely trivial to join any of these things together to generate insights, and they're very rapidly accessible. So let's sort of continue with our story then. We were asking this question, how can we understand this problem of climate change more locally, okay? And for this first, let us return again to our temperature data. And originally we used this for this warming trend, okay? So we aggregated it spatially, we pulled it together to actually on a single point, looked at the time series. But now the question is, if we want to say how are different parts of the US, affected by this in different ways, we want to do a more granular, more local analysis. So what we did for this is we did the same calculation we did early with the time series that gave us this sort of, linear development, this linear growth. And we did this for each point, okay? And we crunched this with pairs. And what we get now is the temperature change over the last 40 years at each point in the United States, okay? So now what you see here is actually a very interesting picture. You see the biggest rises in temperature are in the West. You see California, you see the Rockies, you see, the rest of the West. The East is a bit less pronounced. And then you see development, actually, technically speaking, a part of the North has even gotten a tad colder, okay? And this is something, now you see how suddenly different parts of the country are affected in different ways. We did the same analysis with precipitation, okay? So you look at precipitation and you see precipitation change, again, is regional, okay? We said there was an overall effect, there was a clear point of precipitation growth. But now when you do this analysis more regional, you see there's a very different, how this effect's pronounced against the East versus the West. You see increasing rainfall in the East, decreasing rainfall in the West. And you have to be a bit careful, of course, when you go very local, you use less and less data the more local you get. Obviously, then statistics plays a role. You have to think a bit more about errors, but the regional effects are still sort of hold, okay? You still see that there's definitely things going on in different parts of the country, in different areas of the country. Okay, so this is already progress on what we said before. Instead of having just sort of this, entire aggregate view of the entire country, now we can sort of think about different regions, different areas, what is affecting there. But what we really like to understand is how businesses are affected, how business processes are affected, how supply chains are affected, etc. And I said earlier that pairs processes lots of different data types. And so far, we only looked at data from this PRISM data source. So let's bring in something else. Specifically, let's add to this land use data, okay? So this is land use classification from Copernicus, which is essentially the European Union. Okay, what we see here now is for the same area, how different parts of the country are used. This means, is it forest area? Is it cropland? Is it urban use, etc. Okay, and let me add a few comments. Joining different data types, is actually not entirely trivial. It goes from points like, there's different data providers, different sources, but also things like different resolutions. I told you earlier that the PRISM data we used has a resolution of 4 kilometers. What we're looking at right now is a 100-meter resolution. And if you just want to join these things effortlessly, you have to deal with all these things. And this platform does it for you automatically. Now, how does it deal with our business decision or with our concrete problem to understand better how different things are affected by climate change? Well, what we can now do is we can take this data and pull out, for example, the urban cover. Okay, so how much of the United States is actually covered by urban areas? And we filter this out and we consider the temperature, the precipitation change, now just for these areas which have urban land use. And then you find, for the urban case, all right, we said we have something like 0.024 degrees Celsius per year warming in the entire United States. You'll find actually for the urban areas, it's roughly the same amount, okay, 0.024 as well. However, you find for the rainfall, it's roughly double what is the average across the United States, just by filtering down to these areas, which of course relates to the fact that we said, East versus West is more pronounced, urban areas are more on the coast and certain other areas, so they're not uniformly distributed across the United States. Now, the urban areas are one thing. What is more relevant then is, let's look at agricultural use, cropland, okay? So this, again, we took the European Union data. We filtered out areas, where there is agricultural use. You see very pronounced, the corn belt across the United States. We see agriculture in California. You see, sort of things along the Mississippi and the South. And again, you can take the temperature data, the history we had, the 40 years. You can calculate the change across the entire United States as we did. You filter then to only select these areas with agricultural use. And then again, you find a different insight. Okay, you find that, yes, the United States has an annual warming of something like 0.023 degrees Celsius per year. But, for the agricultural areas, it's actually only 0.014 degrees Celsius. So it's not as heavily affected, which says how growing conditions will change in the next 5 years is different to what you would expect from the rough value. Similarly, for rainfall increases in these areas more heavily, which, should be pretty obvious because we said there was a sort of delineation in rainfall from the east versus the west, more heavy in the east, less heavy in the west, and most of the agriculture is in the Corn Belt. So you see exactly what we saw on these maps earlier. So let me sort of sum up a few things, give a few more comments, okay? So in the last couple of minutes, we showed the web interface to the geospatial big data platform. We were discussing how it pulls in different, data sources in a reasonably simple example still, and how we crunched this data. That means we had this land use data. We compared it with historical weather data, like these temperature time series. We said, you didn't see this live, but we said how the platform that is behind this crunches this data down to do these sort of computations to get you these trends, to then join this with the land use data and give you the idea of what different trends in different areas of the world were depending on land use. Okay. And of course, you could do the similar analysis with, similar things. Either you place your own assets into this and say, how are my assets affected? You could say, how is, for example, corn growing areas affected versus areas where other things are growing? Something like this. Okay. Let me finally give you a few more numbers. As I said, this is a geospatial big data platform. We add lots and lots of data that is relevant to a large audience. So that means we ingest something like 20 terabytes per day. There's a 6 petabyte archive that is ready to use. Clients, analysts can use their own data and add it to it as well for them to join in this analysis and process together. And we use it to power our work in this area, and so do our clients.
So now I'll go into some more detail about our environmental and climate impact modelling framework, which leverages pairs to quantify climate hazards. So we wanted to build a technology to accelerate the process of responding to climate change by better quantifying climate hazards such as floods, droughts and wildfire. And this climate impact modelling framework, CIMF, is a flexible, scalable, cloud-enabled modelling framework designed to onboard, execute and enhance hazard models with AI. These models translate climate variables such as temperature and rainfall into hazards by simulating the dynamics of environmental processes and combining climate and other geospatial data. So the framework contains generic components to enable modelling at scale, so across different spatial scales, across time scales, and across different hazard types. It supports automated workflows to easily onboard, configure, and deploy any environmental or spatial temporal model. So machine learning models, simulation models, hybrid models, etc. And included in this framework are pre-built models, a combination of IBM proprietary models and open source models for impactful hazards such as flood and wildfire. And this is all deployed on scalable hybrid cloud using OpenShift. So let's look in more detail at the components of the framework and how it can be used. Users can quantify hazards by considering pre-configured forecast horizons. So, for example, current climate or a sub-seasonal forecast, seasonal forecast, or future climate conditions. And they can define hazard severity according to configurable metrics. For example, by selecting specific flood depths or durations which are impactful to their application. And another possibility is running what-if scenarios. So, for example, driving a flood model with different extreme rainfall scenarios derived from our weather generator. Another feature is compounding. So this is considering the probability of events occurring simultaneously or in sequence, or different hazards occurring in the same time and place. To support easy model deployment, we have tools to help generate the spatial model domain for a given target location and automate the choice of models and data, and the workflow in terms of running multiple models in sequence. With pre-built hazard models, which I'll show in more detail of in a moment with more in development. And we have modules which use AI in a variety of ways to improve hazard quantification, and I'll show some examples of those as well. But finally, we're building developer tools to support external clients and collaborators in using all the features of the framework, for example, by bringing their own models to run in the framework. So this framework pulls in data from pairs and our own research-developed weather generator and enhanced climate predictions. It can also be connected to external APIs. And the hazard maps generated by the models in the framework are pushed back to pairs to be made available as part of the Environmental Intelligence Suite. So let's have a look in more detail at those pre-built climate hazard models. So I've illustrated here 4 different workflows for 3 different types of flooding and wildfire hazard, which are all available in the framework. These use a diverse range of geospatial data sets and models. So, for example, our pluvial flood workflow uses precipitation, observations, forecasts and scenarios together with geospatial surface features, so elevation, soil and land use. And this are combined to then simulate surface water flooding from heavy rainfall. To quantify coastal flooding, we use NEMO, a physics-based model to simulate storm surge, driven by pressure and wind fields, along with bathymetry data. And then we use LiDAR-derived elevation data to map flood inundation. For fluvial flooding from river overflow, we use an AI model to replace expensive rainfall runoff simulations and predict stream flow. And then we combine this with elevation and river network data to predict inundation. Then finally, for wildfire, we use an open source wildfire model which combines climate and other geospatial data sets to predict a large number of different wildfire metrics according to standard methodology developed in the US, Canada and Australia. So these raw model outputs are all transformed into configurable metrics. So for example, the probability of flood above a certain depth, the number of days with flooding above a certain depth, and the depth simulated for different extreme rainfall events. So how can AI and machine learning help improve and accelerate climate hazard and risk quantification? So here is one example. One challenge in climate hazard quantification is easily validating models against observations or comparing models. So we need to understand how well simulation models reproduce past events before we use them for future predictions. And this can be challenging if ground truth observations aren't easily available. So for example, in the case of flooding, traditionally flood extent information is difficult to obtain. It's inconsistent across geographies, it's not reliably available. But fortunately, we can use remote sensor data to address this and obtain flood extents. And we do this using satellite data combined with geospatial analytics and deep learning. So we then deploy this in the framework and automate this process across geographies and across different flood types. And a further benefit of this ground truth detection is that we can also record historical hazard exposure for retrospective analysis of past events. Another way AI can help is improving simulation models by tuning their parameters to local conditions. So for example, in flood models, surface properties are set from land cover and soil data sets, but these need to be refined to be correct locally. So traditionally, this is done by manual tuning, which is laborious and also doesn't yield optimal results. So using cutting-edge machine learning approaches such as Gaussian processes and Bayesian optimization, we can efficiently tune the models to local conditions and do this in an automated, scalable way. And these parameters can then be used in deploying models to quantify climate hazards. Not only that, but by using Bayesian methods, we can build in uncertainty quantification and predict a range of outcomes according to the uncertainty learned by the machine learning model. But using the framework, we can also combine this uncertainty with climate uncertainty to simulate a whole range of plausible scenarios, providing much richer information. So I'll now hand over to my colleague Blair Edwards to demonstrate how we use the framework to quantify flood risk from extreme rainfall.
Thanks very much, Anne. So today I'm going to be telling you how easy it can be to use the Climate Impact Modeling Framework, or CIMF, that we've developed to calculate hazard risk maps. So in this case, we're going to be looking at pluvial flood risk, and we'll be doing that using a set of historical data, using a climatology. So that involves running a simulation model to calculate the flood risk for a given month of the year, for a set of years, in this case from 1999 until 2018. So when we do that, we will essentially, within the framework, in an automated way, be running all these simulation workflows in an optimized way for every year in parallel, and then combining the outputs. So to start with, we input some packages, and then the first thing we have to do is define the spatial and temporal domain over which we want to run the models. So for a spatial domain, you can see here that we have defined it as a bounding box. In this case, two particular bounding boxes of interest. But you could also do this as a polygon to have flexibility over the area that you want to run the models. As it's a climatology and we're interested in a particular month of the year, we define that month here. So in this case, August. And this will allow us to calculate the start and end days for each simulation run. We can then see and check the bounding boxes that we've defined. And then we can move on to setting up the rest of the simulation workflows. So to do this using CIMF, we have a user-friendly API payload that we can set up. So you can see here, after specifying the type of workflow we're interested in, we tell it the spatial domain, the start date and end dates, the year range that we're interested in, and then we can, in a very straightforward way, tell it the data sets that we wish to use to drive the modeling. So in this case, we tell it the precipitation data, the elevation data, soil and land use that we want to use to drive the models. Then there are some model-dependent parameters, optional parameters that we can set here, and the available options are well documented alongside the framework. So now we've done this, we can then simply submit that to the CIMF API, and that will spin up a model run with these 20 years running in parallel, simulating the different flood scenarios. If we now wanted to do that for a different resolution, for example, with that smaller bounding box, all we would have to change here is the spatial domain, if we wanted to change that, the DEM dataset that we're using, and that will allow us to run at higher resolution. And then if we need to change any additional optional parameters, we can do that too. In the same way, if we were interested in running with different precipitation data, for example, all you would have to do would be to change this entry here in the payload, and the models would be run with the appropriate precipitation data. Again, you would submit that in the same way, and whenever you submit a workflow request, you should get a response giving you an ID related to that tag, to that simulation, which will allow you to track and monitor the status. Status monitoring can be done as well through the API, passing a simple API call. And when the models are finished, that will also return you URLs to download the outputs from the different model runs. So in this case, all the different years that were part of the ensemble. When all the ensemble members are completed, the metrics of flood hazard will be calculated using all the model, the different ensemble members as inputs. If we wish to calculate additional metrics after the fact, we can do that using a simple API call. And here is an example of such a call, where in this case we would be measuring the number of days above a particular flood threshold for 3 different thresholds, and the same here with flood probability, and again with the same 3 thresholds. And you just pass that to the API to have it calculated. Once the metrics have been calculated, they're then uploaded to IBM Pairs, where we can then go to inspect the data further or integrate it in further use cases. So we'll go to Pairs, and we can set up a query like this. And in this case, we're going to set up a query to look at all the input data sets and the output data. So in this case, we have the land cover, the precipitation, elevation, and soil, which are the driving data sets for the model runs, alongside the expected flood days and the flood probability for the 3 different flood depth thresholds that we specified. So now we look at the data, so we can see that we have the elevation data set, which will determine the direction of flow of the water. We have the soil type, and the land cover. And these will be converted into hydrological parameters within the model workflows and feed directly into the model to tell the model again how the water will flow across the surface. We have the precipitation data. In this, just for as an example, this is the total for the month of August for one of the particular years, but it's actually a time series of precipitation that is fed into each model run. And then we have the outputs. So we have the expected number of flood days that we can see here for 15 centimeter threshold, 30 centimeter threshold, or 50 centimeter threshold. So you can see once we have the data in pairs, we can query it alongside a range of other data sets and overlay that to understand what these impacts mean in the real world context and determine the consequences of, in this case, flooding. Thanks very much.
So finally, what are the ways potential external users and clients can interact with our framework? So here are some examples. First, an end user such as an asset manager or a supply chain manager might want to quantify the risk of flooding and other hazards to their physical assets without doing any complex modelling. The entry point for this would be to use pre-configured models and metrics, which could consist of pre-computed hazard maps at different prediction timescales made available via pairs, or pre-configured what-if scenarios for extreme events. Secondly, a risk analyst may want more control over the hazard models without needing extensive climate or impact modelling expertise. They may want to try different data drivers or configure or calibrate models for new locations or do validation or post hoc analytics. And then finally, a data scientist or modeler might be someone who wants to use their own proprietary models with different climate drivers or in a more scalable way, or could bring their models to the framework for onboarding, configuration and deployment. But due to the flexibility of the framework, these models are not even restricted to climate impact models. It could in fact be any spatio-temporal model which consumes geospatial data. So these are all just examples of models of engagement and interaction which we'd welcome the opportunity to explore with you. So please get in touch if you're interested to follow up with us. Thank you.
Excellent. Thank you, Anne and Johannes. And I believe we have them both here live to answer a couple of questions. Nice to see both of you.
Good morning.
Yes, good morning. Good morning. And good afternoon, Anne. So yeah, a few questions in the chat. The first comes from Jen, and the question is, I guess this is for Johannes, what are the computational capabilities of pairs? Like what's a typical runtime, etc. I know you spent a few minutes talking about, petabytes and terabytes, but maybe expand a little bit on that question.
Yeah, thanks. Actually, it's a good point because there's, I think, some nice details about this. Because obviously what we showed in the demo were the results of running queries, okay? So it's a good question, how heavyweight are these things? How much do you have to wait? And so the things we ran, they took sort of in the extreme 8 to 10 minutes to run. And it's good to put this into context. 8 to 10 minutes, you might say, hey, this is maybe the time it takes to make a cup of coffee, but is this like good? Is it bad? What does it mean about this data? So think about it. What did we do? We had some 40 years of daily data. That means we're crunching a time series of something like 15,000 timestamps. Then for each timestamp is actually a map. A map covering conterminous United States at 4-kilometer resolution. That means each timestamp is 500,000 data points. Okay, so roughly the ballpark numbers you want to keep in mind. 40 years. 15,000 elements in the timestamp. For this, we did basically 500,000 linear regressions. And this is before we started joining in the high resolution land use data. Okay, so these are sort of the ballpark numbers to think about to idea computational capabilities. Thank you.
Yeah, wonderful. Thanks for that additional context. I see another question, and it says, we need to let people provide their address and determine, for example, how much insurance goes up, how much is spent on hazard mitigation, growth in property prices, et cetera. And I guess, I mean, certainly insurance companies use, your risk profile is based on where you live. But I wonder, as the technology evolves, as you get even more granular on a geospatial level, this will continue to get more sophisticated, this modeling. Have either of you collaborated or have thoughts on how this technology could be used in the insurance industry, and how maybe getting even more granular will impact folks in that industry?
Yeah, I think
maybe a bit. Yeah.
Yeah, so I think it's a question for both of us. So let me just take a stab at it first, and maybe you add to it, because I think obviously both parts of the story are very relevant there. Obviously the idea to really have access to vast amounts of geospatial data. We heard this a lot this morning already. How crucial data and modeling is to this, and on top of this, the ability to run complex models in SIMP. This is really two things that sort of allow you to sort of quantify risk and see impact, and being able to do this at this very local scale, of course, makes it able to make better decisions. That's what we want to do. Better decisions business-wise. How are my assets affected? One thing is to know, all right, there's going to be a change for the entire United States, for the entire world. But really what we wanted to know and what we're trying to touch on is, as a decision maker in enterprises, but also in government, you said, how are certain things affected? This is always a local question. And this means you have to run these things at high resolution. SIMP can run models at, and correctly, this is a 30-meter we're looking at, at very high resolution, and you can go much finer. We have data up to a few meters down. So yeah, we're going to be able to answer very granular questions that affecting businesses.
Yeah, Johannes, and the other point to make, of course, is that we want to be accurate at that scale as well. So we're using AI to improve our modeling, to introduce that localization to make sure that we're locally accurate as well. And then the beauty of pairs is being able to combine the hazards with all the other geospatial data sets that you need to bring together to quantify the overall risk.
Yeah. While I have you, Anne, I have one, I think, question in listening to your talk specific for you. So, when it comes to collaborating, and I alluded to collaboration at the end, but how would a user bring their model to SIMP? And what kind of models can you actually support in that framework?
Yeah, well, we support any type of computational model. So, we currently have physical simulation models in there, AI models, hybrid models, empirical models based on rules, written in different programming languages, Fortran, Python, for example. And the only requirement is they're containerized. So if a user wanted to come and run their models in our framework, it would just be a case of working with us to create the interface that specifies what the data sets are that it requires, what the parameters are, and then also the requirements in terms of the outputs. So how they might want the output summarized, or do they want raw output, or would the user want this shared via pairs, which would then enable them to do further analytics on it.
Yeah, that's great. And I'll just add, both Larry Light and Allison Davidson can help you connect and collaborate. They put their contact information in the chat, and I encourage you to reach out to either of them or our speakers if you want to try out the technology, bring your models, all the things that Anne and Johannes just mentioned. So with that, I think we're up on our break. Thank you again both for a wonderful presentation. Please stick around if you have some time in the chat. There's a few more questions coming in. I think they'd love to hear from you. And with that, please come back in 5 minutes. We'll come back and continue our program. Okay, welcome back, everyone. I know it's a short break, but we have, again, great content ahead here. The next sessions are going to build upon that foundational work that Johannes and Anne described. Our next session is entitled AI for Better Climate Predictions, and it's a conversation that is led by Campbell Watson, who's a research staff member at the Yorktown Heights Laboratory, and he has two guests with him that I'll allow him to introduce when the session starts. So with that, let's hear from Campbell and the team.
Hi, welcome to the session on AI for Better Climate Predictions. I'm Campbell Watson, a climate and AI scientist and co-lead of the Climate Informatics Research Program at IBM Research. Climate informatics is where climate science meets artificial intelligence. Our aim is to develop core technologies that accelerate the prediction, generation, and understanding of past and future climate events. And we aim to provide seamless predictions across time and space of extreme climate conditions, going from weather to seasonal forecasting and all the way out to long-term climate information. Our final aim is to deliver this data to platforms like PAIRS to drive risk and impact modeling and allow organizations to take action to enhance resiliency to climate change. I'm thrilled to be joined today by my co-lead, Bianca Zadrozny, a fellow IBM researcher in the Brazil lab. Bianca, if you'd like to introduce yourself.
Hi, Campbell. My name is Bianca Zadrozny. I'm a research manager at IBM Research Brazil, and I have been working with Campbell, co-leading the AI for Climate Risk and Impact team that we have in IBM Research. So my background is in machine learning, and over the years I have worked in different projects doing research in applying artificial intelligence and machine learning to different projects in different industries across using geospatial data.
The second person joined by is John Williams from The Weather Company, an IBM business, and very excited that John can join us today. John?
Thank you very much, Campbell. Yes, my name is John Williams. I manage the forecasting sciences team at The Weather Company, which is part of IBM. My background's in mathematics, artificial intelligence, and weather. My team is responsible for using AI and physical science methods to sift through the deluge of environmental data that's available and create the world's best weather forecasts.
So jumping straight into the questions, John, you have a very long history in AI and weather. You were the past chair of the American Meteorological Society Committee for AI Applications, as well as a project scientist at the National Center for Atmospheric Research. And around 7 years ago, you started work with the Weather Company. So can you please tell us a little bit about how your group, the Forecasting Sciences Group, is powering weather forecasting with AI?
Yeah, first of all, I think a lot of people may not know that the Weather Company is part of IBM. And that's really important because weather impacts every business and every individual. So the Weather Company is probably best known for our Weather Channel mobile app and our Weather Underground and weather.com websites, which together serve over 400 million users every month. And we also provide the weather forecast for Google, Facebook, Samsung, and many others, and specialized weather data to over 3,500 businesses around the world, including 40 billion forecasts a day that reach 2.5 billion devices every day. And our Max system drives the vast majority of TV weather broadcasts in the US, as well as many internationally. So IBM is actually the world's leading weather provider. Our forecasts, to get back to your question, they're generated with a combination of automated AI methods with oversight from a group of trained meteorologists. And our fundamental approach is to grab observations and forecasts from modeling centers all over the world, as well as IBM's own global high-resolution atmospheric forecast, or graph. And the AI is designed to correct the forecast based on their past performance, and then blend them together in a way that optimizes the forecast performance at each location, at each lead time, and for each variable. Of course, I'm skipping over a lot of details here, but the upshot is that this approach, AI combined with humans who can nudge the forecasts, like when smoke unexpectedly from the western wildfires blocks the sun and lowers the temperature, This combination creates the best forecasts in the world. And I'm not just saying that. This summer, there was an analysis by an independent service called Forecast Watch that compared the weather company and 16 other providers using only over 80 metrics of accuracy and found that we were the most accurate most often, about 3.5 times more often than our next competitor. And that gap grew every year between 2017 and 2020.
Wow, it's a really interesting combination of automation with things like AI and humans. And I think that gets to the question of dealing with uncertainty. So weather, as we know, weather forecasts, climate as well, inherently uncertain. So how can you ensure or enable smart decisions when there's uncertainty in a forecast?
That's a great question. And when you look at your weather app or your weather forecast, it's not always obvious whether it's a very confident one or whether there's some uncertainty. And of course, a lot of us enjoy looking at what the weather is doing. It's a big topic of water cooler conversations, but really the main reason that we as IBM are in this business is to help people and businesses make better decisions. And uncertainty is a huge part of that. The Weather Enterprise has long focused on what we call decision support, which basically means displaying relevant weather information to users in a digestible form. We're going beyond that with what we call decision services, which move farther up the weather value chain to actually make decision recommendations for a user or even take action automatically. And as you said, uncertainty is a key part of that. Our decisions framework includes 4 questions. First, what could the weather be? How does the weather translate into impacts that a user cares about? And how would the available actions coupled with those impacts affect the outcomes? And then what's the value of each outcome? So just as an illustration, consider a citrus grower faced with a near freezing forecast. How does she decide whether it's worth the expense of deploying misters and blowers to mitigate the risk of crop damage? Well, that depends on the cost of the mitigation, the probability that the temperature will go low enough to significantly damage the crop, which in turn depends on the uncertainty of the temperature forecast. But it's really more than that. You need to know whether the wind will be calm to know if the blowers will help, or if it's dry to know if misters will help. So there are actually a lot of different weather variables at play. So what we've done is to combine and calibrate this large set of over 150 different weather model inputs that we collect from all over the world to create a set of weather scenarios or future weather trajectories at each location and over the next 15 days that are equally likely and span the set of possible outcomes. Each of those weather scenarios can then be translated to its impact on the crop depending on what action is taken, if it's no mitigation, deploying blowers, or deploying misters. And then those results can be fed into a separate model that assigns a value to each outcome, combining the cost of mitigation and the dollar value of crop damage. And by the way, it also matters whether this may be a widespread freeze or a very local one, since if there's widespread crop damage, your harvest will be more valuable. So at the end of the day, each action and each scenario gives an economic outcome value, and you could take the average to find the expected value and choose the best one that's within your risk tolerance.
Yeah.
And I should say that we've developed this probabilistic scenario approach for hourly weather out to 15 days and daily weather out to 7 months in the seasonal time frame.
Yeah, I think from what you're describing, the overlap with climate risk is very clear. And as part of the future of climate research that we're doing, we're focused on predicting and characterizing specifically extreme conditions at these longer timescales, from months, like the seasonal forecast that you just referenced, to years and even decades ahead. And we at IBM Research have been very lucky to work closely with people like John and others at the weather company to develop new technology for sub-seasonal and seasonal forecasts, as well as longer timescales. So Bianca, can you please tell us a little bit about the sub-seasonal to seasonal forecasting technology that your group has been developing?
Yes, so building upon the work of the weather company that John mentioned, our IBM research team has been looking specifically at targeting what we call events that matter. So for example, if you're looking for the likelihood of flooding rains in Southeast USA, or a heat wave in Southern Europe in the span of the next weeks to few months. We are building technology using AI to rapidly create and deploy models for these targeted sub-seasonal to seasonal predictions. And the reason why we think that AI can help in this case is because it even though it's not, in these cases, it's not possible to model very well in like a small scale, like the events, or predict exactly where it's going to rain. The models are able to get information to extract correlations from like long distances relationships, for example, El Nino events, and use that in the model that generates the probability of extreme events. So we have been able to show that it's possible to train these targeted models and get better accuracy than just using the physical models or blending of physical models.
So these models that you're developing for prediction, are they targeted to specific features of the climate system?
Yes. So, for example, we say, for example, we have an extreme precipitation model that is targeted specifically at predicting extreme precipitation. We could also have other models for specifically for heat waves. And as I said, those models, they don't predict, they have some uncertainty built on them. So when we see predictions for a few days ahead or even a few weeks ahead, as John was saying, you have uncertainty and you have multiple possible scenarios that could happen. And what we are trying to do with AI in this case is actually to use what is called generative models to facilitate the creation of scenarios, even in the cases where the signal from the forecast model is very weak. So with that, we rely on what we call what-if scenarios. So in the what-if scenario, a human generates a hypothesis that would be something like, what if you have some a stronger or longer period of rain than expected. So for example, if you have a hurricane that lasts one day more than the one that you just had, and then you could, using generative AI models, you can create very realistic patterns that would simulate that kind of weather pattern based on using historical data and also physical information from the dynamical models, and then generate those patterns that can be fed to the impact model. So we go many times from low resolution information that comes from the forecast and very uncertain information. So you may say you have a certain likelihood of having some extreme rain in this region, to a very detailed map of rain for that region if that condition were to be true. But the thing is that you don't have just one, you have multiple scenarios that are compatible with that hypothesis that you are making. So our tools allow you to generate all these possible realistic scenarios that could be realized, and then you can estimate the risk of different events. So you could use that for wildfire modeling, for flood modeling, for asset damage estimation, using those possible realistic scenarios that could happen under climate change, for example. And another thing, yeah, go ahead.
I was going to say, these what-if scenarios sound incredibly powerful, and I imagine they could also be used for counterfactual analysis. It's similar to what you described with, say, a Hurricane Harvey. What if it lasted for one extra day? What if there was 30% more rainfall? And at the heart of this technology of generating these targeted scenarios is the ability to develop very high resolution weather data that's realistic. So there's a lot of technical challenges in here. Can you just describe briefly some of the ways in which you've been addressing this?
Yes, so the one of the technical challenges is that we rely on historical data to build the weather generators using statistical techniques or AI generative learning techniques. But the fact that they were trained with historical data actually goes against the idea that you want to generate scenarios that have not happened yet. So the way that we are addressing that is by combining this with other techniques from extreme value theory and other ways of trying to extrapolate the scenarios using, for example, physically informed neural networks that could use not only the historical data, but simulate physically possible scenarios. So these are avenues that we are researching right now of how can you actually create realistic scenarios for certain locations for cases that have not actually happened in the past before.
Right, and this technology will be available through the Climate Impact Modeling Framework and also PAIRS, which I think is a really nice way for people to interact and explore possible climate outcomes with our technology. So a final question for John. From your experience of tailoring weather information for decision making, what advice do you have for the audience here with respect to climate risk?
That's a really important question. And, I think we all saw the UN Intergovernmental Panel on Climate Change report this summer, which made clear that we're now in the situation of needing to mitigate the climate change that's already happening. So I think of climate risk as basically future weather risk. And so it's very related to the work that we're doing at the weather company. And of course, we can't accurately forecast what the weather will be months or years in the future. But we can use modeling and AI frameworks to produce a collection of weather scenarios that span the possibilities of what can happen. And then the same decision framework that I outlined earlier still applies. You can evaluate each of your possible actions against the set of scenarios to understand the expected value and the risk associated with each, which then allows you to choose the best actions.
Perfect. So I'm going to end with a call to action. For the first time, the IPCC said it is unequivocal that humans have warmed the skies, the waters, and the lands. But despite their confidence, oftentimes the level of precision needed to take action is not readily available. We need the right tools, the technology, and models in place. The emerging technology, cutting-edge research, and a world-class foundation in weather that we bring at IBM puts us in the right place. So come work with us to build the models and the data needed to understand your vulnerability and exposure to climate change. From rapidly deployable forecast models for extreme events that matter, to what-if weather generators to help you understand the strengths and weaknesses of your organization. We're ready for joint research projects and more. So for more details on how to engage with us, please reach out to Alison, whose details are in the chat, or any of us speakers. John, Bianca, thank you so much for joining us today. Signing out.
Thank you.
Thank you, Campbell. It's a pleasure.
Hey, what a wonderful discussion. And I believe we have Campbell, Bianca, and John on with us. Here they come. 1, 2, 3. Nice to see all of you. Thanks for such a great discussion. There are a few questions in the chat. They're actually, from my point of view, quite related. You talked a lot in your discussion about uncertainty and confidence, because taking action has a cost. So whether you take that action will depend a lot on how confident you are in the models. So let's start with Paul's questions, where he asks, what is the state of the science with respect to how far out we can reliably predict weather risk to meaningfully inform mitigations of risk?
Sure, I can take that. So I started to type a response to you, Paul, but I'll just answer it verbally. Key things here are what type of weather risk, what are you what sort of actions are you wanting to take? And what's your uncertainty threshold? Things like, will the temperature be getting warmer? I think the state of the science is pretty clear. Yes, absolutely. But is that useful for the risk that you're trying to mitigate? If indeed, the question is more like, what is the likelihood of receiving 100 millimeters of rainfall on a given day in a specific location in this particular decade? There's a little more uncertainty with that. We can certainly say things about trends and put uncertainty bounds on that. But a lot of it has to do with well-defined questions. So the way I'd respond to it is, for some things where uncertainty is a little too high, we prefer sort of a counterfactual or climate storyline approach for these long-term projections, where you'd actually pin the specific event you're interested in to larger scale dynamics or circulation. So it might be atmospheric rivers hitting the coastline of the West Coast US, and trying to tie, let's say, relatively local features of the climate to specific events, and then searching through, say, CMIP6 archives data for these larger scale events like atmospheric rivers that we know are relatively well resolved in the models. So yeah, but it's a great question, and it's something that I think more of a consultancy role, like we have with our GBS group, is something that can really come into play to help people with that.
Yeah, I think there's actually a good follow-up to that. We talked about working directly with businesses comes from, I believe it's Olivier, who asks, do you have practical examples of correlating weather scenarios with the performances of business processes of an enterprise and of predicting process KPIs according to various weather conditions? So very, very to the point. So I'm curious, any thoughts on this question?
I think that's maybe for John.
Yeah, I thought so too.
Yeah, so that's a great question, and we've worked with different industries, and each one is different. I think one of the really interesting ones was working with a major airline who was interested in making decisions about whether to delay or cancel flights the day before, and so depending on what the weather is at the airport and what the FAA says about how many aircraft you can land, you have to decide which of all the many flights you could make you are going to make. And if you can proactively delay or cancel your flights the night before, then you can save a lot of money and time. If you catch people before they head to the airport, you can reschedule them. So that was just a really interesting example of where our scenarios went into determining the airport capacity, which then went into the flight planning, and the airline has, of course, models for how to do that. And then at the end of the day, the ability to compare different playbooks. So I can't give you, a precise KPI or maybe even a cookbook for how to do that. It's going to depend on the industry. But I think we do believe that this scenario-based framework can be really powerful.
That's great. I think so. Thank you for that detailed answer. I think we're just up on time, but please do stick around in the chat if you can. There are a few other questions. I think the attendees would love to hear more from you. Thank you for the discussion and for your the thoughtful discussion and for answering the questions that we got to, and just thanks for participating. I'm looking forward to seeing you guys in the near future.
It's a pleasure. Thank you.
Thanks, George.
Yeah, absolutely. So we're going to move on to our next speakers. We have Jitendra Singh and Schmidt Marvania, who are both research scientists from our India lab and are focused on the Future of Climate initiative. The title of their talk is Climate Aware Applications, Demand Forecasting. So with that, let's let them begin.
Welcome to our session on climate aware applications. My name is Jitendra Singh, and I'm a research scientist at IBM Research. I'm a part of leadership team of the Future of Climate initiative, focusing on climate-informed applications. In this role, I'm passionate about infusing weather and climate insights into enterprise applications to make them resilient against weather and climate risks. During this session, my colleague Smith and I will be discussing these applications and demand forecasting We encourage your questions throughout our presentation, which you can type into the chat. Or at the end of the presentation, we will have time for a couple of questions as well. So let's get started. Thanks, Smith, for joining me today for discussion. Could you briefly introduce yourself?
Hi, Jiten. Hi, everyone. I am Smith Marwanya. I'm also a research staff member at IBM Research. My work focuses on building innovative research applications for many real-world insights using NLP, ML, AI, and computer vision in the areas of education, agriculture, and supply chain. Over the last year, we have been building climate-aware capabilities such as multi-horizon uncertainty-aware demand forecasting, and also how to enable climate forecast explainable to enable resiliency in supply chain.
Awesome. Smith, can you explain at a high level what are climate-aware applications? What do you mean by that?
Sure. The climate-aware application basically means the enterprise application in which the operational and planning decisions are significantly impacted or influenced by weather and climate at multiple timescales. There are many applications in supply chain and asset management, such as demand and out-of-stock forecasting, inspection and maintenance, which are impacted due to climate change. Traditionally, this application did not utilize weather and climate insights fully, as we already experiencing significant climate change in terms of changing weather patterns and weather extremes such as heat wave, cold wave, storm, flood. Climate resiliency has become a significant imperative for businesses, and climate-aware application could help them achieve that.
Okay, so to narrow down the topic a little bit, let us pick supply chains. What do you mean by climate resiliency in the context of supply chains?
Sure. Let us first look at few events of climate and weather impacts on supply chain, which are fairly recent. As you can see on the slide, on the left-hand side, energy supply chain. Last year in September 2020, we saw severe blackout due to record-breaking electricity demand in Texas due to a heat wave. The energy supply chain got disrupted due to significantly increase of usage of cooling system. Similarly, in February 2021, millions of people left their homes and they were without power and water due to deadly winter storm. Similarly, on the right chart, as you can see, in 2020, fashion and apparel retail products suffered from low sales and high inventories due to pandemic. However, in November 2020, Delhi region significantly experienced the coolest temperature in a decade that resulted in increase of consumer demand for winter clothes. This example shows how disruptive extreme events can impact supply chain resiliency in a big way. Due to climate change, such events are projected to be more frequent and intense. Our research is focusing on building resiliency against such events so that businesses are prepared to address them in a proactive manner rather than the reactive one.
Climate resiliency and adaptation is indeed in the top of the mind for everyone. Could you talk about how climate resiliency is connected with climate-aware demand forecasting?
Sure. This is an important question. As you know, demand forecasting is a key first step in supply chain operations such as demand and inventory planning, precision planning. Climate-aware demand forecasting use weather and climate data in an intelligent way along with other informations such as holidays or product information to forecast the demand. Thanks to advances in weather and climate science over the last decades, weather and climate events can be forecasted more reliably and accurate much ahead of time.
There are multiple solutions available commercially and also in the open source. Could you share what are the limitations of those solutions and why can't they be used in the context of climate change?
Sure, it's a good question. The state-of-the-art forecasting technique do incorporate short-term weather attributes along with other parameters, but in a deterministic manner. However, these approaches do not model uncertainties or probabilistic nature of weather and climate, which is the most important factor in the context of climate change. Hence, the forecast made by these existing approaches may not be accurate and hence reliable enough for informed decision making. So one has to come up with an innovative approach that models uncertainties in both space and time while building demand forecasting applications. This has been our research focus, and we have got very good success in this by building uncertainty aware neural network models. This model basically learns the uncertainty in input space from a large volume of geospatial weather and climate data as a part of model development.
Okay, so what are the technical challenges in building such models? And how is IBM best positioned to address these challenges?
This is a very good question. Definitely, we need an infrastructure to manage large volume of geospatial data. For this, we have a big geospatial analytics platform called Pairs to manage all this data in an efficient manner. We also have access to best-in-class weather data from the weather company, which is IBM owned, as well as from other forecasting agencies such as ECMWF. At IBM Research, we have a dedicated research group focusing on further improving weather and climate forecast, prediction of extreme events such as flood, storm, heat wave, cold wave. Besides this, we also have deep expertise in artificial intelligence that is required to model this complex data for various downstream applications.
Can you explain how climate-aware demand forecasting can benefit users or businesses?
Sure, there are many impactful real-world applications that can benefit from climate-aware forecasting and specifically demand forecasting. Here is one such scenario for retail supply chain. As you can see on the screen, retail manager typically plan for high volume sales event in advance, such as Black Friday or Christmas. In this chart, you see two forecasts generated with and without climate data for the product category of thermal clothing. The height of the bars shows the amount of errors for predicted demand. The blue bar represents the prediction error for climate aware model, whereas orange bars represents the prediction error for non-climate model. As you can notice, the model with climate insights shows improved forecast as you closer to the Black Friday event. These forecast insights can be useful for retail managers for more informed planning of demand and inventories up to 6 weeks ahead of time. Similarly, precision planning for seasonal goods require more lead time and accurate demand estimation a few months ahead of accounting for changes in weather patterns such as early winter or late summer. Climate-aware demand forecasting could bring economic benefits for these use cases as well.
This is interesting. What research innovations are needed in building scalable climate-aware forecasting?
This is a very important question. There are two core components which need to be considered while designing and developing climate-aware forecasting solution. First, we develop a scalable climate data pipeline which is integrated with Pairs, which is a geospatial analytics platform. The climate data pipeline enables data download, data processing, extracting customized uncertainty-aware derived features, support for use case inspired features. To give an example, we want to derive features related to heatwave for a particular location and the time frame. For this, we need the weather data for the period of interest and also the historical climatology data representing what happened over last 20 to 30 years. This data pipeline are designed in a way so that all these operations are done in an automated manner. Second, we design a modular neural architecture that include a set of subneural networks to specifically model the individual weather or climatic features extracted from our climate data pipeline, and also simultaneously learn the spatiotemporal complex relationships between different types of features and the target variable, such as demand.
Thank you for sharing the research innovations and example use cases. I can see a lot of benefits and utility in the supply chain management. But what could be the other use cases outside of supply chains where this solution can be used?
Excellent question. Yes, in fact, there are many use cases of climate-aware forecasting in food supply chain, such as production forecasting that we are currently exploring. Similarly, new use cases are emerging in energy supply chain related to increased renewable power integration in the grid. Given that renewables such as wind and solar are intermittent in nature, power and demand forecast at multiple timescale is crucial for load balancing and grid stability. Our demand forecasting solution, leveraging artificial intelligence, can be used in this context for enhanced renewable integration and grid operations.
This is very interesting, and I can also see how AI can help in better forecasting. However, with these sophisticated deep learning models that you referred, there is also a concern of explainability and trust of these models. Are you also looking at these aspects of the AI models? Also, what are your future plans, direction of research on this topic?
Absolutely. Thanks, Jiten, for asking this. As a part of future work, we are building tools to enable climate-aware forecast explainable so that users or subject matter experts can take decision confidently. For this, we have explored explainability toolkit AX 360 that we plan to use and enhance while learning a reasoning knowledge graph to allow user to do interactive what-if queries in an intelligent way. Further, we are also exploring advanced AI technique to learn use case inspired feature representations that will reduce the dependency on domain specific data. Furthermore, this advanced AI technique do not require handcrafting of features, which is a time-consuming activity in building the models. We are also planning to expand to other applications in energy supply chain.
This is exciting future directions and research. Thank you, Smith, for an interesting discussion, and also to our audience for listening today. Thank you again.
Okay, excellent. And we should have our speakers on, Jitendra and Schmidt. Nice to see both of you. How are you doing?
Hi, George. Good morning.
Hi.
Hi. Good.
Good morning.
Good. So a couple of questions in the chat. Let's start with Jen, who says, can you integrate other demographic or social data, such as population and region-specific buying patterns in climate-aware demand forecasting capabilities? So can folks bring their data sets, I guess, is the main question.
Yeah, sure. So I think from the geospatial data perspective, I guess it's we can integrate many forms of geospatial data in a seamless way because of the infrastructure pairs that we have to manage and curate such data sets. Also, the underlying models that we are talking, I guess they are independent of any specific data. So they can also integrate such data in the feature space and then do the forecasting. So the answer is yes for this.
Yeah. A question from Olivier, who says, is it possible to forecast the demand for electric cars, for instance, depending on medium-term global warming or the evolution of temperatures at a country level? Any thoughts on electric car demand?
Ismet, do you want to respond? Yeah, I think it's definitely possible, but I guess for this use case, there would be many other factors like policies and things like that. But definitely here, I see that even the temperatures and evolving weather patterns could help improve, plus the policy signatures included in the model as well. So yeah, I think it's a nice example to try it out as well.
Yeah, I bet the mind share also improves the demand there, right? I mean, people know that we all have to do our part, and so electrification of our vehicles is one thing you do. Were you going to say something, Schmidt? I don't know if I cut you off.
Yeah, definitely, George. So this is a very good question, right? As electric car definitely needs the for charging, right? You need the power to charge your battery, and how your input source is dependent on, right? Whether it is really reliable on your renewables, or whether it is reliable on the maybe some other power sources. And we do see that efficiently forecasting the energy demand in the domain of the electricity or energy, which could actually help you to forecast the usage of the electric car, as well as like how often they are going to charge, and how much is the energy demand which is going to be needed for this specific use case. So this is definitely going to be the future. I mean, like in the domain of the environmental sustainability, as well as in the electric car perspective. Yeah.
Yeah, I hadn't thought about the infrastructure piece when I saw his question, but that's an excellent point. Thank you for bringing that up. We have, let's get to one last question. We're a minute over, but I do want to get to Rachel's question, where she asks, you mentioned using demand forecasting for load balancing. Could that do enough balancing to support an entirely renewable energy grid, which is actually related a bit to your previous answer, Schmidt, but any of you want to take that question?
Yeah, definitely, because as we even gave few examples, right? Because of the heat waves as well as the cold waves, right? The usage of some of the electrical, the equipments is like increasing significantly higher, right? So how can we efficiently estimate the peaks of the energy demand and plan much ahead of time, so that some of the blackouts kind of the events would not happen? And how can we have sufficient the power in the backup, so that we can enable the resiliency as well as the stock out kind of the scenarios in a real world situation, right? So definitely using the climate data and accurately forecasting this kind of applications have a lot of potentials to enable the resiliency even in the domain of energy and utilities. And subject matter experts can take appropriate decision making by how much is the additional demand is going to be because of what kind of climatic the change or extreme events. Yeah, it's a very powerful tool.
Great. I think we're a couple minutes over, so I will leave it at that. There are a couple additional questions in the chat, so if either of you have a few minutes to go in and interact with our audience, that would be wonderful. Thank you again for a great presentation and for joining us live for a great discussion. I appreciate it.
Thank you, George. Thanks, Smith.
Yeah, thanks, Ethan. Thanks, everyone.
Thank you. So we'll go on to our next session, which is led by my colleague, Leventi Klein, who's a research scientist here at the Yorktown Heights Research Center, working in geospatial analytics. The title of his presentation is Climate-Aware Applications, Decarbonizing the Electricity Grid. So with that, let's hear from Leventi.
Renewable energy is the dominant energy source that is generated in many parts of the world. In Europe, there are countries where more than 40 or 50% of the total energy is generated from renewable energy sources like wind, solar, hydro, or from natural gas. In the United States, the overall percentage is around 10% of the total energy that is coming from renewable. It is known that traditional energy sources like coal or fossil fuel is generating around 1 kilograms of carbon dioxide for every kilowatt hour. In order to improve the carbon footprint of the electric grid and also the energy generations, there is a need for a higher integrations of renewable energy sources in the overall energy generations across the globe. With the increased penetrations of the energy coming from renewable energy, it has been observed that the overall cost of the generations is decreasing. This trend has been demonstrated across the last decade, and indeed, nowadays, the energy produced from renewable sources are going to be comparable in price with other types of generations. In general, there are a couple of things that are driving this one. Overall decrease in the cost of the productions that it's coming from cheaper solar panels and wind turbines that could be easily integrated into the electric grid. And many of the technologies that are making the integrations are also decreased in price. But renewable energy has its own challenges. There are intermittency that is generated in many cases from these energy sources, meaning that the power that is generated at a certain moment of the day, it's going to exceed what is going to be the demand. But some other parts of the day, the generations of the renewable energy may be very tiny or inexistent. Such the case would be, for example, if it's a cloudy days or it's a wind-free days in various parts of the world. Also, there is a mismatch between what are the ideal locations for generations of energy sources and also where is the highest demand for this type of energy. So, for example, locations in the United States that are ideal for solar radiation and for solar power generations are going to be in Nevada or in Texas, but the highest demand for energy is going to be on the coast, which are most populated. So there are multiple ways in which we could address the price drop of the renewable energy sources. There could be potentially new transmission lines that could be built in order to move the generations of the power to the locations where it's a high demand for it. But that tend to be relatively expensive as it requires investment in the infrastructure, in the power lines and the transmission infrastructure that is going to carry such power. There's also a need for energy storage, mainly coming as batteries. As the batteries are integrated into the electric grid, they are going to be take up the excess of power that is generated in certain locations and then provide this energy at the moment when the demand is going to be very high. Both the transmission line and also the integrations of batteries are relatively expensive technologies. One way in which we could address the cost drop for renewable energy is potentially to have better forecasting. Better forecasting, it's really going to provide an understanding about what is the availability of the power at every moment of time. And at the same time, the same forecasting tools also could predict what is going to be the consumptions at different moments of the time. Now, in order to generate reliable energy forecasting, multiple data sets needs to be combined. And those are coming in the form of, for example, weather models. It's going to be satellite observations. It could be Internet of Things type of sensors on the ground like weather stations. Combination of these data sources could provide the possibility to increase the granularity of the forecasting, extend the time horizon, and improve the overall accuracy. IBM developed a technology called pairs, that it's a big data platform that it's able to take various data sources and then do spatial temporal analytics on some of these data sets. Combinations of various data sources, it enables the pairs technology to improve the forecasting that is generated from renewable energy sources like the solar and wind, and at the same time apply advanced machine learning analytics to improve the local forecasting at the specific locations on the globe. So some snapshots of the technology, it's shown where we could analyze, for example, the wind forecasting and understand what is the best locations where, for example, a wind farm could be placed. And based on historical data and also some forecasting that is coming from climate models or weather data, we are able to identify the best locations where these farms are going to produce maximum of energy, such that now the investment could have a return of investment shorter compared with other locations. In order to do this, we have to analyze the weather data, for example, wind, and also the variability of these conditions across multiple timescales, and also analyze it geographically to identify the locations. Also, we could combine this information with satellite informations in order to analyze what is going to be, for example, cloud cover, and then predict what is the best locations for solar generations, and then try to match the production with the demand at various places across the continental US. As these data sets are combined, we have better ways or tools that are using advanced machine learning techniques, physics, and also statistical methods in order to identify what would be the uncertainty in some of these predictions. And as one example, you can see here, it's going to be the cloudiness, or how much sunniness it's going to be in a certain location versus the time horizon. As we are extending the time horizon, we are going to observe that the uncertainty is increasing, bringing a larger error. And also some of these laws are going to show some exponential dependencies, meaning that as we are expanding the time, the uncertainty is increasing. Also, we have power law distributions. Combination of these techniques into an overall framework like pairs technology enable us to do quantifiable power forecasting for every location on the globe, and at the same time quantify the uncertainty. This type of information could be used by energy and utility industry to better plan where to generate the power, when, and what would be the best conditions to meet the generations with the demand that is coming from the consumers. Our first example or demo is going to be around solar radiation forecasting. Using the pairs geoscope tool, we are going to visualize, based on information coming from various weather models, the distributions of the solar power availability across the continental United States. What we are going to see that some areas that are depicted here in red are showing regions where the potential for solar radiations is increasingly high, while areas that are going to be blue are showing regions where the solar radiation is going to be significantly lower. The variability is coming from the cloud cover that is detected on every day. We could analyze the time series for these particular data sets in order to understand what is going to be the variability every single day. And some days we are going to observe that there is going to be maximum solar power generations, while other days are going to show some decreased generations due to the cloud coverness. This variability is going to be geographically dependent. Region in Nevada is going to show high productions, while areas on the east coast or even on the northern part are going to show much smaller small solar radiations that is generated. All this information is really related to some fundamental physics coming from the cloud cover. At the moment that there is high cloud cover, it's going to be much lower solar radiations available for generations, while areas where we have much smaller cloud cover is going to generate more solar radiations. This variability is going to be seasonally dependent and is going to show areas where we have consistently much lower cloudness, for example in Nevada or in Texas area, while other areas are going to show increased variability or cloud cover that is going to be in the northwest or is going to be on the east coast. In general, the power productions in the ideal places are characterized by regions where the population's density is going to be relatively small. So what we see in this particular graph is going to be the distributions of the people per square kilometers, and red regions are going to show areas where the density of populations decreased. These are really the areas where the highest demand for generation for energy is going to be high, and accordingly we have to match the demand with the productions. What tools like pairs geoscope can do in this particular case is the possibility to go and match the production with the demand. By analyzing patterns and historical data about what is the demand for energy in various locations, and then placing a distributed solar panel or solar farms in those particular areas, we could decrease the overall demand and at the same time match the production with the demand. In doing this type of technologies, we could plan accordingly what would be the best area to place some of those solar panels, and at the same time enable energy and utility industry to better manage what is the overall productions of the energy, what would be the best way of the distributions, and what's going to be the best way for the transmissions. Our second demo is going to focus on wind forecasting for the state of Texas. Data from the pairs technology could reveal the spatial patterns of the locations that are ideal for wind power forecasting. As you can see in the below map, regions that are going to be red or yellower in colors are regions with a high probability of having high wind speeds and the directions of the wind to be consistent. Other areas that are represented by the blue or the greenish region is going to show a much higher variability both in the wind and also in the wind directions. Time series analyses are going to show that there are some seasonal patterns. In the springtime and the winter time, it's going to be a high variability in the wind speed, while in the summertime, it's going to be a much lower variability. There are also spatial distributions, so nearby the Gulf of Mexico, we are going to have higher wind, while in other regions, for example, in the southern Texas, it's going to be less availability of the wind for generations of the wind power. The spatial patterns could be taken into account in order to better design where to place the generations of the wind power, and at the same time to optimize such that the constructions of new transmission lines or the distributions could be minimized at the same time. Now, wind at the same time, it's also a risk factor. Many areas are going to have increased fuel availability, and the wind can drive in various locations wildfire appearances and then distributions. Some of these wildfires can interrupt the productions of the wind power or the wind power distributions, and a comprehensive view needs to be taken in order to understand what is the best locations for where the wind power could be generated, and at the same time minimize various risks that are coming from the wildfire. And in this particular image, we're going to see some areas that are going to be red in color, indicating that those regions are going to have very low risk of the wildfire, and they may be also close to the locations where there is a high availability of the wind for the generations of the sources. For a utility company, both the generations of the power and the possibility to distribute to various customers is going to be highly important. So in order to maximize the consumptions of the renewable energy or the wind energy in this particular case, some of these built close to the distributions or the transmissions and the distribution wires, such that we could maximize the overall consumptions of the power generated by the demand coming from the customers. And in order to do that, we could analyze information related to the distributions of the assets that could be observed for a particular areas, and analyze how some of this information in conjunction with the possibility to generate maximum powers could be matched locally, and then use smart grid technology in order to better manage the demand and also the forecasting type of technologies, such that we could minimize the overall waste of the power in various locations. And overall, these new technologies could enable companies in energy and utility industry to better manage their availability of the power. Overall, the renewable energy forecasting, it's one of the advanced tools that enable a smart grid operations. Many of the technologies that are required for smart grid, for example, variable pricing of the energy or also demand forecasting, really require a better understanding of what is the availability of the power at every single moment of time, and combine that one with a demand that is coming from the consumers. Big data technology, like the one provided by pairs, provide us the tools to better forecast at a higher granularity, both space in time, and also reduce the uncertainty or the error in such predictions. Combinations of various sources that is enabled by pairs technology, it's opening the way to lower the overall cost of renewable energy, and at the same time reduce the overall carbon footprint of the electric grid.
Wonderful. So I believe we have Leventi on. Hello, sir. How are you? Good to see you.
Good to see you.
Good to see you too. A couple of questions in the chat, but one that I've very curious about myself is about network resiliency and I suppose efficiency. As we do have one giant monolith grid, another option could be to have microgrids that are local. Kind of what are the trade-offs between those two from, say, a resiliency point of view, from a cost point of view? I'm really curious to hear your thoughts on that.
So that's an excellent question, George. I think that the idea is that if you look, we have the electric grid, right? And it's already there, so we can take advantage of it, in many parts of the United States. Building, microgrid, it's really just an investment that local communities needs to do. So they have to really come up with the generations, which is mainly going to come from solar. And then they're going to need some type of storage where they're going to be able to take this type of energy, right, and store it for the moment when they're not going to be able to generate. So from resiliency perspective, you can imagine that if you have a microgrid and it's like a huge outage for the whole grid, you can still maintain the power. So you would have continuous power on, but that's certainly going to come at a cost. If you want to have certainly you're connected to the higher grid, then potentially the cost going to be smaller, but at the same time, you're going to have higher risk of managing, the power. So you're relying on the utility companies to provide this power for you.
Yeah. Are there any examples of that happening in the US, for example? I'm not aware of any personally, but are there any?
There are a couple of examples in Brooklyn.
Yeah.
So I've seen examples where small communities, they started to form, and essentially they made the investment of generations and then also the storage. And they are trying to somehow fence themselves from the electric grid. And it's a viable option. It's more popular in Europe right now than it is in the US. But examples of working and doable, it's certainly something that it's out there. And it's probably going to be the future.
Oh, that's really interesting. I wonder how that'll be interesting to see how that all plays out. Great. And then I guess this is more of a general question, but there's a cost associated with decarbonization. And so I guess, what's your view on that? I mean, how do we best estimate that? How do we prepare for that going, down the road?
So, I mean, there are various policies that are out there. So mainly coming from the US government, that it's proposing that by 2035, we are going to have a carbon-free electric grid and electric generations. And there are various studies that are coming from government agencies that are looking into how much it would really cost. And it turned out that with just a few $1 billion investment, less than $10 billion, we should really transition by 2035, probably to a carbon-free electric grid. And that's going to require potentially more solar, more wind, and eliminating some of the older generations that is coming from coal and then the fossil fuels, and potentially increase also the overall balance of the nuclear energy such that we are able to compensate for these intermittencies or variability in the generations that it's coming from the solar and wind.
Yeah, it sounds like policymakers are going to have a big role in that as well. Hey, we're a couple minutes over. Thanks again for the great presentation and for the time you took to answer questions. Feel free to hop in the chat. There are a couple other questions there from the audience. I'm sure they'd love to hear from you. Thanks. Great. Thank you. So we are now on to the final session of the day. We have a panel discussion. This panel is led by Bianca Zadrozny, who is a senior manager in spatiotemporal modeling research out of our Brazil laboratory. And she's going to actually introduce our three panelists today that come from various that are industry leaders in their respective industries. So let's turn it over to Bianca and the panelists.
Hi, everyone. Thank you for the introduction, George. As you said, we are glad to have with us today three business leaders who share with us their perspectives on how their industries are responding to climate risk and how they are adapting to reduce impacts as best as possible. So I'll start by introducing Hagen Hench, who serves as the director of the Distribution Operating Center West at One Electric Delivery. So Hagen's organization is responsible for monitoring and operating the western half of Encore's electricity distribution system, which serves approximately 3.5 million customers. In this capacity, he provides oversight over day-to-day system operations and service restorations efforts, as well as change leadership and process engineering for technology implementations. So Hagen, to start, can you please tell us more about Encore operations and how they are affected by extreme weather events caused by climate change?
I would love to. Thanks for having us on this panel, Bianca. And just to give the audience a little bit of background, Encore is a transmission and distribution utility in the northern part of Texas. So we are a part of the ERCOT grid, and we are a platform or delivery provider only. We do not generate electricity, we do not sell electricity, but we are basically the transportation system in our service territory that transports the electric commodity from the generators to the end users. As such an open delivery platform, we're really technology or generation agnostic, and what commodities are being used to generate, or what technologies or end consumption is taking place on the other side of the grid. So keep that in mind as I'm sharing our view and perspective, how we respond to weather events, climate change, disasters, in order to reliably operate our grid. I'm obviously coming from a delivery platform perspective predominantly. And as you might imagine, this delivery grid that we are talking about, the large transmission long distance lines, the inner community distribution feeders are highly exposed to their environment, to any weather situations, just as much as to human activity, construction activity, drilling, driving. All those factors, not just climate and weather, affect the delivery of our services. So thanks for having us.
Thank you. I will now introduce Brad Gammon, CEO of Earth Solutions, a company that provides a software as a service platform for energy, gas and electric utility, municipality, telecom, and media industries to help ensure the reliability of critical network infrastructure. Before joining Earth as CEO, Brad was Global Managing Director of IBM's Energy, Environment, and Utility Industry, and he has also previously served on the boards of the Terawatt Initiative and the Paulson Institute's Council on Sustainable Urbanization. He was the founder of the Global Intelligent Utility Network Coalition and a founding member of the Gridwise Alliance. Brad, can you tell us how the industries served by Earth are being affected by climate change, and what is the role of the technology you provide on their adaptation?
So enjoy being on the panel, particularly glad to see Hagen. It's been a little bit, so I'm actually glad to see Hagen. We've had the opportunity to collaborate in the past. So critical network infrastructure is kind of something that people walk over or walk around every day and don't, I think, have the fullest understanding until there is an outage of some kind or a disruption of service. That its criticality to delivering the energy transition, which is, decarbonization is heavily going to be driven by automobiles going electric and power sources that Encore delivers from the wind fields or the solar being delivered reliably across. Our software company and many others are focused on how do you ensure that you understand risk, and where we're focused on to that infrastructure, and that can come in a number of ways. Where we grew up is ensuring that when someone excavates or does construction, that those facilities are not damaged. But as we're moving into the future for the industry, it's key to understand how climate events can affect that infrastructure itself and damaging it. Protecting current infrastructure, our gas pipeline systems here in the U.S. with methane released every year equals about 69 million cars on the road just from methane coming out of our long-haul gas distribution networks. So there's the side of identifying things that you can control now that are basically failures of the infrastructure as it sits today that can be corrected, but also how do you have the right information to make the best use of investment into growing the infrastructure, whether it's electric infrastructure, primarily the electric and distributed energy resources, to lead us to a carbon neutral future as far as the grid goes. Understanding how climate will impact, how economic growth in particular areas He's going to create density of use where electric vehicles will deploy more quickly. Understanding how that infrastructure needs to be protected to allow that to happen is very important, both for external risks and physical risk from those particular assets. And so that kind of what I would call insights that technology like IBM provides from pairs combined with other data sets starts allowing you to have a much more economical way to start viewing risks and adaptations that need to be made to that infrastructure to protect it.
Thank you, Brad. So now we go to Jared Westheim, who is Vice President in Goldman Sachs Sustainable Finance Group, where he advances work across divisions in sustainable data and analytics, corporate decarbonization, climate risk, and climate-related investments. Jared received a master's degrees from Harvard Kennedy School, where he focused on climate policy and finance, using winning a university-wide prize for his work in environmental economics, on climate change finance, and working as a Dukakis Fellow on environmental markets in the California government's office. So Jared, could you give us a brief overview about sustainable finance and how it actually facilitates good investment decisions in the face of climate change?
Great question, and it's a pleasure to be here today. So I think broadly what we're seeing is a transition in financial markets that's taking place, where there has been a growing awareness, given, I think, increasing secular trends, of the importance of incorporating particularly non-financial risk into financial risk assessments when you're making lending decisions, when you're making investment decisions. And there's no area that's actually more important for that incorporation than on climate risk. And I think, over the long term, physical climate risk in particular, which has the potential to really change structurally the nature of how capital markets work, how risk and return will be realized, what our major growth assumptions should look like, how much volatility will occur across the marketplace, and even things as distant as inflation and how that will impact elements like probabilities of default and rates across the lending markets. So a lot of what the work that I do is to think about how we can take the information from the climate science community and actually incorporate it into a variety of decisions that we're making across our institution. And a lot of our peers are on similar journeys. And so what I'll describe is really not unique to Goldman. It's rather, I think, a broader, set of trends that we're seeing realized across the financial markets. The first is really across our risk division, really thinking about how physical risk can be incorporated into lending decisions, what level of concentration appetite we actually have for various physical risks across our portfolio, and similarly, how that interacts with transition risk and what sort of transition risks our lending might be exposed to in the future and how we want to mitigate that on a forward-looking basis. We're also thinking about how to apply scenario analysis into broader investment decisions that we're doing on the basis of our client touches. And that involves looking at things like, how do we actually think about changes to the structural macroeconomic environment on a go-forward basis? Do we think that there is going to be substantial, as I mentioned, long-term volatility or depressed growth due to physical risk changes that will impact the broader environment? How will that impact larger asset class changes, whether that actually impacts the breakdown, for example, of how emerging markets might be able to perform versus developed markets? What should that mean for our investors? And then in the context of specific investing portfolios, really thinking through granular investment decisions about, is there particular concentration risk associated with municipalities, with sovereigns, with corporates that might be actually exposed to physical risk in a particularly asymmetric way? Could there be clustered events or concentrated events that might actually cause us to realize substantial losses if a particular set of climate scenarios occurs. And I point you, to Hurricane Ida, or what's happened in the past across the Gulf in terms of hurricane impacts, as in increasing in frequency and intensity, but also the industrial cluster issues that we saw around the oil and gas sector with the recent event that has caused a lot of production to go offline, or let's say the Texas event that we saw more recently related to shock freezing happening across utilities. And all of those things are required for us to address from a system resiliency and an evaluation of how that might actually impact financial returns from an institutional perspective.
Thank you, Jared. That was very interesting. So I'll go back to Hagen now to ask if you can give us a little more detail about the kinds of technologies that you currently use, the advanced analytics that you actually are employing now at Encore to predict damage and risk. If you can go into a little bit more detail on that, that would be helpful.
Yeah, that's a very good question, but I also think it is important when we look at what opportunities we have to deploy technology, advanced analytics, all these things that allow us to make better and more intelligent decisions, more proactively anticipate and respond to these circumstances that we're talking about here. Then it's important to see what type of decision do we try to impact. Just like any infrastructure operational organization, you can roughly organize your thoughts in three categories. How do we plan an infrastructure system to better withstand environmental factors, especially if they occur at a higher frequency, at a higher severity, those kind of things? How do we need to reevaluate our design standards, our design approach, what kind of technologies and equipment is available that we can incorporate into our grid to make this grid more resilient? So those are very basic and very important decisions, both to Jared's and Brad's comments, that will naturally evolve over time as this informed view that we have of the future will now inform investment decisions on our assets and incorporate technologies that may have not been available in the past. So the data, the insights that we are generating from both our predictions, from our forecast, what we expect to happen down the road, will inform our today's investment decisions, how we design structurally, topographically, as well as from a technology and an equipment perspective. So how can we incorporate more automation? The business cases will change. Some of that technology may have been available in the past, but now with a revised view on the frequency and the severity of events, you now have a better business case at a larger scale for deployment. Technologies, the cost of technologies, the life cycle cost, all those kind of things have an effect on how we look at our investment decisions around the grid. That's one category. The second category is a little bit more focused on specific prevention. Many people talk about grid hardening. Where do we want to invest in underground facilities? Where do we still want to be exposed on the overhead side? What kind of redundancy can we incorporate and go back into our existing facilities and saying what kind of measures can we take that will help us to better withstand any kind of events, whatever nature that may be. So that these two categories are well-established practices where the new insights and data flow in to drive and inform these decisions. And lastly, of course, technology and analytics, for that matter, has a big impact on how we respond to these events. So it's not just planning or a specific event prevention, but now we're talking about how can we better respond to events? How do we gather insights from our environment, the situational awareness, how we deploy our resources, how do we understand what situation we're facing on our system, so that we can have a more effective and a faster restoration response associated with any kind of disaster. So So that's high level kind of the categories, and then we can dive in each of those categories and saying, okay, so what specific technology, what specific data points do we have? What kind of activities can we identify here? And there's many examples. If I go on the disaster response area as well as on the prevention side, I want to piggyback a little bit on what Levente shared earlier. It's not just the utilities' internal data sets that drive that. So what we're getting back from our equipment, the meters, the SCADA equipment, our crews, there's a lot of data points that we are collecting that inform our decisions and that we can analyze to drive better decisions. But it's also the remote sensing and environmental data sets that we can receive from the outside. And I think a very promising technology there is clearly satellite deployments that really have changed in the past years. There are lots of new satellites, new data coming back, and it is particularly interesting in that field because it is so broad scaled. So if you think of a large transmission and distribution system like Encore's, we're dealing with almost 140,000 miles of lines. There's a lot of possibilities when we look at one particular location, what we can do and how we analyze it, but it becomes very challenging to identify the high risk and the response options when you look at it at scale over 140,000 miles. There's limits how many eyes you can put on a system like this at the same time, just physical limitations. And so through remote sensing, satellite imagery that is detailed enough and produces actionable insights for us, there's a lot of opportunity there that allows to quickly identify those areas that deserve the human attention, deserve resources. Another example is obviously in the planning area, where we really try to identify what is the population growth, especially here in North Texas. We are overwhelmed by just the investment volume, both on the commercial and residential side. We are connecting almost 100,000 meters new every calendar year. Just keeping up with the construction volume changes the topography of the grid. How do we augment the system to address both accommodate the growth that is taking place, as well as the operational risk challenges due to weathers. So it's not a siloed only decision that all we are doing is only geared towards accommodating a big hurricane or tornadoes or a bad winter storm. Our decisions obviously are also influenced by where can we accommodate the new growth, how we can get a timely construction completed to address new factories, new homes, new subdivisions, and all these things funnel together. And you can see how data analytics and complex modeling really helps us to make better decisions in all those areas.
Thanks. Just to complement in this planning decision, how far in the future do you do planning for Encore? I mean, it's like how many years ahead do you start planning a new transmission, or can you complement a little bit on that?
Yes, I mean, as you might expect in any business, you have different stages in your planning horizons. So we would typically go out probably no further than 5 years. That's a realistic planning horizon for us. Just the uncertainty increases dramatically if we go past that horizon. So, and then you take it back, you have your high level plans, you expect where your growth areas are around your metropolitan areas, where new subdivisions, new growth will take place based on land use, so you identify your redevelopment areas, your expansive new development, all those things, and you get a general idea in what direction the growth in a population center, which is different in the rural areas versus in the metropolitan areas. So you have a general understanding where your growth goes, and you try to position your facilities to accommodate that growth without incurring the risk of stranded investments where you're building overcapacity where you're burdening your ratepayers with costs that we shouldn't. So that's kind of the long-term view, what I call 5 years. Then you bring it down to you revisit that every year, and then you basically have an annual review where you're revising your plan and make specific construction scopes that then will be executed to expand the capacity in areas, to improve the reliability due to maintenance, or to accommodate specific customer requests that require construction. And so the annual plan then is what we execute, but it's all based on the 5-year plan that goes out.
Thanks. So going out to Brad, Hagen mentioned that the availability of new data sources, like more satellites, is could help in their case to be able to more proactively make predictions, also assessments of damage to have a faster response. So in your case for Earth, can you mention a little bit about the kinds of data sources, sensors, satellites, etc., that you use, and how you see changing in the future, the types of data for monitoring and response?
Yeah, Hagen's exactly right, and it also plays into some comments Jared made, is to really take advantage of the period of time we're in, where heavy investments going into infrastructure in North America. The infrastructure bill has $73 billion in it just for grid infrastructure, if that happens. So we're in a period of time where there's a focus is how do you spend that well to reinforce the current infrastructure against climate impact, and also a different growth pattern in our economy right now, where that should be placed properly to manage risk. I think it's also interesting right now, and I'll get to the data, that there's also mass support for deployment of 5G across the country. And what's interesting is that smart grids and telecom go together at the same time, because you have to have the communication infrastructure in order for an intelligent grid to be more responsive and reactive and resilient in the way it operates. So to this kind of asymmetric point that Jared brought up, these linear networks are all linked together. It's the telecom network, it's the electric network itself. As we learned in Texas, how you're protecting the gas infrastructure matters, because that's a key fuel, for balance of the stability of the grid itself. When you start looking at that, it means you need to look at this linear infrastructure that delivers these services holistically. And the only way to do that is look at all the potential risks that are out there. It's the age of the assets that are out there that the utility companies own. It's the changing climate conditions. It's not just storms. If you move out to the west, it's temperature of the ground, where you have pipelines buried potentially, and you have rising ground temperature that can affect the fidelity of pipelines themselves and the delivery of their services. So being able to merge together climate information, current information of the environment that the physical asset is sitting in, understanding the complementary nature of those different services coming together in a region and how they have to work together to be resilient, to deliver the full service. I call them fused systems, is bringing all that data together in a view that you can then query against scenarios of what would happen today, what would happen 5 years from now, and start judging economic impact. What kind of industries are in that area? How critical are the industries and the logistics they provide and the goods they provide? Well, I think that's really important to bring that together, is then that helps you direct investment. It helps the utilities of the world make better cases to regulators. Banks put pressure on, and financial investors also, of where they see the need. In order to deploy capital, you've got to have insurance that the economic vitality is there. You need to understand what social services are in those areas and understand impact like that. So I think this whole area of fusing all these different data sources of what's the economy in that area look like, what is the environment, what's the physical infrastructure, what is climate change going to do, bringing those together in a way that you can analyze and plan is very, very, very important. for the way cities plan, the way banks plan, the way utilities plan. And that's something we're very focused on, working with a company like IBM. But how do you bring those data sources together and make it easily queryable so you can start doing the kind of analysis in the planning phase, if you're trying to basically adapt, or the things you want to be doing right now to mitigate, like I mentioned with pipelines, where you've got, leaking pipes of methane that are kind of undoing all the good you're doing with wind farms in West Texas. Or when you have a big power outage in California or in the third world, you start turning on diesel generators en masse. And there's in the developing world, there's about 300 gigawatts of diesel generators there that, again, offset all the good work done in other places if you don't have a reliable electric grid. So I think data is at the core of, how we go into this more sustainable future.
Thanks, Brad. That makes a lot of sense. I like the example of the pipeline temperature, soil temperature. So going to back to Jared, I think that you can also add some perspective in terms of the kinds of data that you use in your within financial. So in the same sense that Brad and Hagen commented, can you give us a little bit overview of what kinds of data set do you and different sources and also types of data do you incorporate, and how you do that for different problems in the financial industry?
Yeah, absolutely. So, I mean, when we think about physical risk, I tend to break down the world in a similar way that the insurance industry has broken down the world historically, which is you have hazards, which are what, particular companies might be exposed to. How is the climate going to change? What is the increased frequency of flooding, of extreme heat events, both chronic and acute? And then you have exposures. So are your companies actually located in a particular area where those hazards occur? And then finally, you have vulnerabilities. And so vulnerabilities are, let's say that you have an asset that is exposed in a particular area to a particular hazard, and that hazard occurs. What's the actual damages that are going to take place contingent on that, chain of logic and that hazard occurring? And it turns out, I think, that we have a pretty good way as financial institutions, and increasingly good technology that's out there on the hazard end. There are a lot of different companies that are serving the financial services industry to really think about how is the climate going to change? How does that actually materialize at a more localized geospatial level? What does that look like in terms of multi-hazard events and different frequencies occurring? How can we think about that in terms of broad-based or broad-brushed geographic exposure? But one of the things we don't have very well right now is actually on this front of knowing where the locations of some of the companies that are invested in are. As you can appreciate, this is not something that's probably that is widely disclosed across all industries. There are sometimes national security implications involved in that public disclosure. Sometimes there are economic competitiveness implications involved in that disclosure. And there isn't really a disclosure standard or a method for financial institutions to actually get access to those geospatial locations. So there are emerging, developing data sets out there that allow us to look at where some types of businesses might be located. But even when we can actually locate those businesses and know where the facilities are, we often don't know how important those facilities are, which is another critical step in the logic chain. So if a facility gets hit, is that 80% of production? Is that 10% of production for a particular company? How important is that from the perspective of financial disruption if a hurricane comes through and takes that production offline? That's a question we can't easily answer right now, and has a lot to do with the lack of facility exposure data. And then finally, we get to the vulnerability end of things, which arguably to me, from a financial institutional perspective, is actually the most important for us to understand, but also the hardest piece of information for us to get access to, which is what actually makes a company vulnerable. And Hagen and Brad have actually done a really good job of kind of laying out a lot of the interdependencies when it comes to broad-based, grid resilience, and some of the interdependencies on things like fiber optic networks, and actually understanding a long value chain in terms of how it's installed, what some of the underlying resiliency conditions of a grid might look like. And that's something that we may not have access to from the perspective of a financial institution, but it is actually something that we can have influence over. So when we talk to companies and when we engage with companies, one of the most positive points of engagement we can make as a financial institution is actually to talk to companies about enhancing their resiliency, issuing specific financing that will allow them to actually increase the level of resiliency that they've, and adaptation that they've built into their systems, whether that's a grid or location of a generation, location of their generation, moving it from a basement to a third floor in a flood-prone district. There are plenty of examples out there that we've kind of explored to actually be able to, not only think about assessing risk, but building resilience. And that's an area where I think we do need things like new types of disclosed information, disclosure standards potentially, to really understand what are the actual adaptation and vulnerability actions that can be taken in partnership with the companies that we lend and invest to in order to build that resilience over the long term. One thing I'd quickly add here is that nowhere, in my opinion, is this more important than when we think about the concentration of risk in emerging markets. When we think about resilience and adaptation and the ability of developers companies to the physical risk, one of the critical dynamics here is that physical risk will show up in an asymmetric manner for a variety of reasons across developing countries. Now, does that mean we should disengage from those developing countries entirely because they have higher risk concentrations on the physical end? I worked in emerging markets for years, and my contention would be no. One of the things that we need to understand is what we can concretely do to actually build resilience and enhance the financing so that we don't have those physical impacts in the future. But without those deeper understandings of what is actually driving vulnerability, what actually is a proactive adaptation response, it becomes an exercise where we just look at risk and don't actually think about the things we can do about it as financial institutions.
Yeah, that was actually a very good perspective, right? That you don't just want to estimate risk to make decisions, but you actually can cause change by actually helping people address the vulnerabilities, and that's very, very interesting. So going back to Hagen, can you tell us a little bit about what you see, going more into since we're closing now, what you think would be like the future, let's say the perfect future for Encore in terms of both the response and planning that you mentioned before, in terms of how the technology would evolve and how the operations would run?
Well, I think in many ways, I just realized this, to be honest, in many ways, as an operational manager in a grid company, we really look at the world in our grid very similar to how Jared described how he looks at his investments. So if in many ways, however we augment, however we invest in our grid, and for that matter, even how we operate and run our facilities today, is very much how Jared would look at his portfolio of investments. So all these factors that he describes are exactly the same factors that we have to look at with every investment decisions that we make on our grid, and for that matter, it's a life cycle decision that includes maintenance, life cycle costs, what is happening down the road, as well as upfront from an asset perspective. So in many ways, the drivers to make good or better investment decisions in a changing and uncertain world are very much the same. And so if you're asking me what would be the perfect world look like, is that I have data on everything and the perfect algorithm that eliminates that uncertainty so that we can investment decision with a high degree of certainty without the risk of stranded investments or underinvestment in the areas where we should have done more. So more data and more intelligence to turn that data into reliably actionable information. So that's the perfect future that I pray for. But obviously that is impossible. But what we're dealing with is we are making progress in that direction. On one side, I think we all recognize it's not just climate change, it's changing customer expectations, it's changing technology, it's the changing society, how we use electricity, how we depend on electricity. 20 years ago, if you lived in the country, you had a different attitude towards your electric service than you have if you live in a metropolitan area, in a connected life. So that there's a lot of changes around us that are going on that are driving these uncertainties and driving the change that we need to adapt to as we provide any infrastructure service or make investment decisions. And so what we are making progress there. On one side, there is the volatility because of the intermittency of renewable generation, of all the change that is going on around us. So the uncertainty is increasing and makes our investment less attractive and more uncertain, and it's less quantifiable than maybe in the predictable world of the past. On the other side, we're producing more data. We are having promising technological advancements that now can address that uncertainty and the volatility that we feel. And so we really need to watch both sides, predict and understand these changes that are going on around us with open eyes, and then really not just make investments in our infrastructure itself, but also recognize the value of information and data that allows us to make more informed decision on those assets. So in the past, there's an intangible assets called data that was just a cost center. Now we're recognizing data to be more of an asset because it allows us to address and minimize risk and uncertainty in our investment decisions. And so that's the future we're moving towards. The volatility will continue to increase the uncertainty, but we're also producing more data and more technology that allows us to manage and handle that volatility. And that's a little bit conceptual, but I think it finds its expression in those three categories that I outlined earlier. We're making better planning and investment decisions. We are smarter how we can prevent and harden our grid. So data and technology will help with that. And we are smarter and better in how we respond to disasters by having data available, having people with mobile devices out there, having satellite images out there. So in all three categories, we're getting better. And so each company needs to gauge itself. How are we making progress? How are we exposed to these uncertainties? And then how, with our data investments, with our intelligence, the insights that we're gaining, how can we address that to bring that risk back down to stay attractive for our investors?
Thanks, Ada. So, okay, guys, I'll give also Brad and Jared a chance to wrap up as we're running out of time. So I'll please, Brad, if you can also mention a little bit more. I like your or you mentioned about 5G and how this is going to impact the kinds of decisions that we make. So if you can mention that in your final words.
I think Hagen summarized very well. It's just, I think you've got to look at the interrelatedness between these physical networks, whether it's the 5G, gas, electric, and also transportation networks, the rail systems and the road systems, and those interdependencies between those have to go into a risk assessment to vitality of industry and community behind those networks and the way you look at them. And so Hagen said it perfectly, that to do that efficiently and effectively, and I think the term he used, reliable information, trusted, because if you're in the finance area or you're an actuarial in the insurance industry, it's about trusted data. And that's what we're very focused on and working with companies like IBM is how do you get the trusted data across these things to make good decisions with.
Jared?
Yeah, I think just in terms of, high level summary of some of where we are and where we should go, the journey for financial institutions really, I think, started, very recently on physical risk. So it was really, I think, accelerated and brought to a lot of people's attention, 6 or 7 years ago. And so it's a relatively new field. And when that all kicked off, the focus was on awareness. How do we build awareness of physical risks as a factor within financial institutions? And I think many of us, most of us, are painfully aware of physical risk dynamics being real, affecting financial markets in a variety of ways and creating systemic risk. And I think where we're at right now is trying to find out new ways to use the data and broader universe of resources, including engagement with companies, to move quickly from awareness to impact. Thinking about what we can concretely do to make change. How do we execute actions that are going to build real resilience? And what is going to be the unique role of financial institutions in connection with corporates around the world and municipalities and sovereigns in building that resilience over a longer period of time?
Thank you very much. It was a great pleasure talking to you three today. I hope everyone else has enjoyed as well. So I think, Hendrik, now you can go back to George. Okay.
No, thanks. Thanks, Bianca, and thanks, Brad, Jared, and Hagen for a really wonderful conversation, a very insightful conversation, and thanks for participating in our event. I'm going to turn it over actually to Hendrik. Hendrik opened our event, and he's going to close our day here. Hey, Hendrik. Those of you that weren't there in the morning, Hendrik is our chief scientist in our Future of Climate, and I will leave it to Hendrik to close out our day.
Yeah, so I guess I have the impossible task to conclude today's sessions. I always like to look back and summarize what sticked, and of course, I will not be thorough because we just heard too much. But if you recall our first keynote speaker, I think reminded us quite well about the human dimensions of the impact of climate change, right? It's not just about the numbers. It has real impact on people, on businesses. He also reminded us of that we can only be successful if we collaborate. Now, the geospatial analytics and impact, this demonstration by Anne, I felt made clear how impact modeling has become so easy, so quick. Now, it's never quick enough and easy enough, but we're really catching up what Hagen described and Jared described with the increased volatility, and technologies trying to keep up with addressing some of that. They also show quite nicely how it has increased the accuracy of the predictions, right? And how it enables to understand the context of climate impact information, right? The vulnerability in these questions. The presentation by Campbell and the chat with Campbell, Bianca, and John, reminded us that IBM is actually the leading weather forecasting company, right? Using AI for a long time. But it's not just about the weather, right? It's much more. It's about the decisions you're making. And we also learned how we can address that challenge of uncertainty, which is inherent to forecast, but how we can actually use that information also to make better decisions. The application discussions by Jitendra and Smith and Levente, and of course a great panel we just had with Jared, Brad, and Hagen, also gave us a little insight on the real applications, how to adapt to the impact of climate change. So it's not just theoretical, right? It is about the right decisions. It's about preparing. Tomorrow, we are not done. So tomorrow we have an exciting agenda where we actually look at the role of the public sector. And we'll kick off with Donald Wibbles, who is a professor at UIUC. He is a presidential fellow. He's a contributor to the Intergovernmental Panel for Climate Change, so you cannot miss that, right? Make sure you're coming back. There will be a second keynote with a very intriguing title, The Climate Dance in the Triple Helix, by Lux Research, also by an excellent speaker. We'll then hear from two leaders from IBM, Kumi and Shantanu, about our technologies. And of course, we're also going to conclude with an exciting panel tomorrow with government leaders. So let me close by thanking all the participants. Thanks so much, the speakers, panelists, for all your contributions. And we see you tomorrow. Thank you.